Welcome to this session, and we will call upon Kanak Saha from IUCA, who has done some wonderful work with using UVIT, and I know, as you'll hear, about very high redshift galaxies that he discovered and published in Nature and all. So welcome to Kanak Saha.
Hello. Hello. Good morning. First of all, I thank the organizer for providing me this opportunity to present research that I have carried out with AstroSat UVIT. I don't know how much feedback I have on AstroSat, but AstroSat has given me a sort of a new dimension in my research career since it was launched. And in this, I'm going to today talk about what we call an AstroSat UV deep field. And my talk will be sort of divided into three parts. First, I'll give you a very quick overview on the deep field observation, and then key highlights. Particularly, I'll just talk about the galaxy growth because there will be like other talks, and then I'll spend quite a bit of time on the cosmic reionization problem, and that's what we've been addressing with the deep field data. So this was the observation carried out in 2016 and centered on the Chandra deep field south. And this is the part where we have the AstroSat UV deep field data, and these are the two fields we observed as part of the GT time, and Sham gave me the opportunity to use this observation. And the two filters, as you know, in the far ultraviolet and near ultraviolet are the observations. So this is basically focused on the good south field, and this is what the AstroSat UV deep field looks like. This part is basically we call the deep part, where we have our 64 kiloseconds of data, and this is the shallow part where we have our 33 kiloseconds of data. Originally, it was proposed to have about 50 kiloseconds and 50 kiloseconds, and should have a overlap region which should have 100 kiloseconds, but recovery was not not 100%, but it was 60-70% of the data. And this is what we have right now. And these are all some of the famous HUDF, Hubble Ultra Deep Field, and in which we have some of the data. And this is what it looks like in 4-color image. And so it covers basically what we present here is a 236 square minute of area in the sky. And in near ultraviolet, you have 62 kiloseconds. In far ultraviolet, we have 64 kiloseconds. And the depth that we reach here is a 27.7 magnitude in near ultraviolet, which is quite impressive. And in far ultraviolet, we reach a 27.2 magnitude, 3 sigma depth. And we have some detection of the sources, about 19,000 in near ultraviolet and 13,000. And we have to do this astrometric accuracy by hand, and then that we got into about 0.2 arc seconds and about half a pixel. And this is some of the comparisons which you can see. This is the AstroSat, and this is the HST near IR filter, 160, 1.6 micron. This is what the galaxy looks like. You can clearly see quite an amazing improvement in the deep field survey. And then you can also look at very exciting object. This is an elliptical galaxy. You can see here at redshift 0.27, and we have at the center we have AstroSat the observation, and this is in the interacting spiral galaxy, which you can see in JWST, and one can study that using AstroSat deep field data. But of course, we have not used those data for look at the nearby galaxies, but we look at only the far galaxy. There was an important part which required to get into the observations very carefully. We needed background measurement, because the standard software that is normally used, which is called the source extractor software, if you use on AstroSat far ultraviolet data, because it is a very sparse field, it's a low photon counting image, you often end up getting a zero background. So we needed, we sort of developed with one of my students, Pushpak, who actually made this is the simulation where we increase the lambda is the Poissonian random field, and it is of the low photon counting and the high photon counting, and then we have used number of sources. This is less crowded, this is crowded field, and then we sort of analyze this to get into we developed a method which is based on the minima in the 2D, two-dimensional field, and we show that our method were much more actually recovery was much better in estimating a background. So we have published a paper on using a geometric approach to calculate the background. And so this is the background map, which you can see clearly the Poissonian nature of the photon counting mode very clearly, and then from which we estimate the background. And this is the background map which goes into the deep field observations. Catalog preparations we have done in a different way of hot mode and cold mode. So in the cold mode, you see only the bright sources. In a hot mode, you can see bright and the faint, and both the sources you can find. And this is sort of the number density histogram. You can see this is where the 3 sigma detection limit, and in near ultraviolet, you go up to around 27.7 magnitude. And this is the completeness analysis in the photometric completeness analysis, where we inject sources, artificial sources, and we see how much we can recover. And you can see also the 50% completeness are by this, and the 90% completeness around 26 magnitude. So that's our completeness. And there is another important thing that we have done with the deep field observation is the spurious detection noise peak. So now how do you know a certain part of the image that you see is a source or not source? So that's a very important thing. So first one you see here, it's basically done on negative image. So you just take the image, invert it, and then see whether there will be detection. And we see only 2 such sources being detected in that, so we are very confident. And then these are this histogram shows the source detection on the real data. This is the source detection on a artificial simulated data. So we have sort of taken the Poissonian random field and created a simulated image, and on that we run the detection algorithm, and you can see that this is as you can see in around 27 magnitudes. So if we have a source which is around 27 magnitude, so you can say that okay, this much is the contamination. So this is a big problem, as you will see this later part of my talk. That is a very important aspect being often by us. So we have a AstroSat UV deep field website now, and all right. So first I'll go to the first part of my talk, is a galaxy growth. So we know the galaxy grows. If you look at the JWST from redshift 13 or 14 to there, and this is the sort of in the middle part of the sort of redshift 1 to 2. So the shape of the galaxy is more clumpy. So you can see that this is more matured galaxy in the local universe. And so galaxies basically are not stationary, they grow. And they are growing through the different ways. So the typical route are a hierarchical structure formation scenario. One of them where 2 galaxies merge, and sort of if nothing goes out, so there will be the doubling or adding the mass together. And then in this, there will be one important aspect that we'll see is that every time a galaxy merges with another, there will be chemical inhomogeneity. And sort of the imprint is like a foreign body comes to the galaxy. They come with their own metallicity, own metal content, and they get mixed in the galaxy. And then there is some way we can sort of identify this. The other one is more like a galactic ecosystems where the gas comes from the filament and comes to the galaxy and sort of makes stars, and sort of these stars clumps sort of go in. See the M83, you can see the H1 gas, and they would sort of form stars in the outer part of the galaxy in terms of a clumps, and these clumps would move in and sort of help the galaxy growing. And this is what I call Atmanirbhar galaxy building. All right, jokes apart. So this is sort of evidence for the sort of that Atmanirbhar galaxy building. And this is, I would say, the one of the key discovery of galaxy discovery, where you see that wherever there is a H1 gas, you see sort of stars forming. So this is called XUV, extended UV emission in galaxies, around galaxies. And then we had this from the AstroSat. So this was done XUV in the local universe, sort of redshift less than 0.1. And this is the paper where Anshuman, one of the PhD students from Tezpur University, worked with me. And you can see the clumps in the outer part of the galaxy. This is the optical part. And this is where first time we say that XUV beyond local universe. So this was published in 2022 in Nature. And then you can see like another, the distant XUV, so we are sort of like looking at this mode of the galaxy growth, which will become more and more important in a higher redshift range. And Pushpak's talk at redshift 0.67 of an XUV. Now I come to the last part of my talk, where we talk about the cosmic reionization problem, and this is why I started actually this deep field observation. And as you can see, like as a photon like greater than 13.6 electron volt energy hits an hydrogen atom, it gets like ionize the hydrogen atom. This is an insignificant phenomena, but it has a tremendous impact on understanding our universe. And in this, there will be this ionizing photons, Lyman continuum photons, extreme, they are all same. They all come under the bracket of energy greater than 13.6 electron volts. And and you can see that I'm not going to go into this detail. This is where the cosmic microwave, and then where sort of you can think that this is where mostly the hydrogen gas, and soon after that, universe went to a dark age, and then as first stars, first galaxies started forming, which were emitting copious amounts of like neutral, ionizing photons. They would start ionizing the gas between the galaxies. So this is how this is how the reionization era started, and it sort of ended around redshift around 6. And the question was basically, how do you like what are the sources and how did this happen? So I'll go into this a little bit. So this is where you can see the evolution of the neutral hydrogen fraction. This is what we said. This is the time since the Big Bang, or in the redshift from 10 to like go. So it is almost like a phase transitions, but it is actually not. You can see these are the observations which show that like these phase transitions sort of from hydrogen gas being from neutral to ionized phase, sort of probably going gradually. But it's now the most recent data suggests that hydrogen gas or the reionization was complete by around redshift 5.5 based on the recent quasars observation. Now, sort of we talk about the key issue, the astrophysics part of it, where we talk about the photon budget. So this is the photon budget. So this comes with a multiplication of the 3 factors, the rho UV, the UV like density, and then multiplied by the ionizing photon projection efficiency. And then once you have that, then there is this quantity which is called the F escape. So this is what all 3 needed to actually get an ionizing photon budget for the reionization problem. Now, we have the UV luminosity function. So from redshift 6 to all the way up to 10, based on the JW, we can also have JWST. You can also have UV luminosity function, and then you integrate it, you get the rho UV. So that's not a difficult problem. And we also have from AstroSat, we used actually to constrain the rho UV from low redshift to like high. Of course, this is where we don't have the AstroSat data. We have only niche is like up to redshift 1. So we have published about 2 papers on UV luminosity function. And then the second part, which is the ionizing photon production efficiency, which like we can say that they are mostly like a massive young stars, OB stars, maybe POP3. So this part is quite an unknown actually. So you depend on the model. So this is the binary stellar population ionizing intrinsic spectrum. And this is where the Lyman limit, this is a 912 angstrom. And below 912 angstrom is completely opaque. So we do not know, we do not have any idea about the galactic spectrum in this part of the spectrum actually. And then we do not know, that is why it's very difficult to understand the ionization photon production from the galaxy. Then the notorious quantity is the escape fraction. The escape fraction is basically ratio of two quantity. So number of ionizing photons that is produced in the galaxy, and then number of ionizing photons that is escaped. So it's basically simple ratio of the two quantity. If you want to calculate this number of ionizing photons that is escaped, so that we can use like with the direct measurements. We need the direct measurements. And then this one, the denominator depends on all your models. So basically like ionizing intrinsic spectrum, the geometry of the ISM, the dust properties and everything. And once these photons are produced in the galaxy, they need to be transported. So this is the radiative transport problem. So this is the complexity in F escape measurements. So the first thing is basically you can look at the Stromgen sphere, where you can think about that this is the ionizing photon production. Most of the ionizing photons will be absorbed by the hydrogen gas which is surrounding them. So only way possible that this ionizing photons comes out is there must be some kind of a low density gas and dust which is through channel made or like holes in the Stromgen sphere through which the ionizing photons comes out. But if you can compute the mean free path, then it comes out to be like much less than the size of a galaxy, and we say that, okay, there is no ionizing photons getting out of the galaxy actually. Then there is another problem that if some ionizing photons comes out of the galaxy, then from the source, you need to travel a long distance to come to us. This is the IgM problem. And this IgM problem, people have worked out a lot, and this is the model where you see the simulation, Monte Carlo simulation, showing that you put in the hydrogen gas clouds and see how many photons can travel to you. And by the time around redshift 6, you can say that there is no ionizing photons basically getting out of the, like, reaching you. So it's a again, very difficult the problem, and that is why before AstroSat, these are the observations started only in 2016. This is in 2018. So there was nothing basically in between redshift, like around 0.3 to 0.24, and people have done like galax data and sort of stacking all the galax data and sort of said no detection actually between redshift 1 and 2. So we use the AstroSat filters to use the these two filters, far ultraviolet and near ultraviolet, to get the ionizing photons like coming out of the source, and sort of this is a bit complex. And after the AstroSat, we have the first detection, and this is the first detection of ionizing photon between redshift sort of desert here and at 600 angstrom. So this is the first detection. And then I think I'm going to skip a bit in the interest of time. This was the galaxy which we discovered in 2020, and I'm going to skip this. And this galaxy sort of, we had the first escape fraction measurements, which is around 20% of the ionizing photons that come out of the galaxy. Now, after that, we sort of, many of my students, Suraj, Somil, did his PhD, and we are sort of populating this part. In this, you see the escape fraction versus the redshift, and this is the part we have like from the AstroSat only. We have now 17 plus detection, and this is a very unique capability that we are sort of probing 500 to 600 angstrom photons first time using AstroSat, and no other mission can do this at the moment. Now, of course, like now I'm coming close to, so beyond redshift 1 to 2, we gone on to redshift 3, and there are some clear detection there, but I did not get into that. So it's a low-hanging fruits, no. So there is, I give a slightly glimpse about the redshift 6. As you can see, I remind you that at redshift 6, so this is a textbook that says that by redshift 6, no photons will come out. So it says like almost all papers start with that. And then so I thought of doing this problem. So don't look at this one. This is the analytic, so the Lyman Valley, using the, see that how many, whether there's a possibility of transmission and then catching the photons. And this is the Monte Carlo simulations from there. And then I sort of stacked galaxies and see at 600 angstrom from here to here and see no detection. This is the deepest HST field ever. And then from 700 to 800 angstrom, I use the Muse IFU to create a narrowband and see no detection. And then 500 to 700 SPM using 435 filter of HST. This is the one. And then you see no detection. It goes as per this graph. Okay, so we thought like, maybe there will be a transmissions here. We could like sort of use this problem. So we did a stacking experiment using 10 galaxy, and these are the 5 gold galaxy where we see JWST spectra. Very well, and these are the where Muse Lyman alpha emissions are there, and then we have the excellent detections of 8.5 sigma from redshift 6. And then said, okay, what's wrong? Maybe there is something wrong with this. So I started going to the HST UV stacking also. This is the HST UV 275 filter. This is 336 filter. So which means that we have now simultaneous detection at redshift 6, 3 filters, completely 2 different instruments, 2 different systematics. And to validate this, I have done a lot of experiments to whether like, so I'm not going to go into that, but it is like, to me, it's like AstroSat, HST, Muse, IFU, and JWST is like a nice symphony, all work together to give me this detection at redshift 6. This is currently under review. Hopefully something will come out soon. And I'm close to end. So these are like a lot of my student postdocs who have worked with me and my collaborators from outside. So I'll thank all of them. And please look at some of the talks and posters of like some of the students, postdocs who worked with me in the last several years, and I sort of thank them. I'm sorry.
Yeah. So the time for 2 quick questions. Yeah.
Thank you. That was a wonderful talk. Just one concern. When, for using Sextractor, you said that you had background 0. So I didn't quite understand how is it that you were adding the background, and if you were adding the background, were you undermining the UV flux that you're getting from the sources? So that's the question that I had.
So if you look at the UV, the far ultraviolet images, you will see most of the time you have zeros basically. Zeros and then like very few photon. And if you run source extractor does like background calculation using mode, which is basically combination of some mean and median, and it gives you basically 0 background in that. And so that's basically then you will be underestimated, but the background is there. So we used now we sort of did the smoothing and did some like some analysis sort of. I'm not sure I can get into that, but I can talk about this definitely. But there is a way now we have a background calculation method in such low photon counting mode.
Any more questions? Okay, if not, yeah, okay, please.
So Sextractor assumes the background is Gaussian. So that's to answer you.
Yes.
But the question is, what was the hot and cold mode of detections that you've shown in the?
So the gold model is basically see one of this detection of the Lyman continuum detection.
Sorry, the hot and cold model of detection.
Hot and cold. So the cold is basically where you raise the threshold very high, so that you detect only the bright sources. In hot mode, you get into basically the noise part. You reduce the threshold per pixel, and you can detect like many more sources. And sometimes, for example, a galaxy and a small clump, something that you will also add as a source. But then you have to cross-match whether they are part of it or not. So, but main difference in the hot and cold mode is the detection threshold. So in the hot mode, you detect like many noise peaks and everything, but in cold mode, no. Cold mode is more secure.
Okay, I have just one comment. Whenever S60 and all are looking at different field, UVIT is many times open. So you have a lot of surveys available for exploitation, doing medium sensitivity surveys and deep, because we are routinely, at least for S60 observations with prime instrument, you can have many fields with 20,000 second to 60,000 second exposure with UVIT. And so people who want to get into, there is a lot of nuggets, lying around in many other observations in which UVT may not be the prime instrument. But if it has been configured, the data is available. So I would encourage people to look into these things, and especially the young students.
Yes.
Yeah. And thanks for a wonderful talk. So our next speaker is Kameshwar Rao, who is, I think, well known to the UVIT community with his lot of work on various spectroscopic aspects of all kinds of objects, planetary nebula and so on, which has been pursuing all his life. In fact, he was one of the first persons to encourage the making of UVIT for AstroSat before he retired.
Okay. Okay, thank you.
Welcome to Kameshwar Rao.
Thank you very much. Good morning. And this is a topic, there is not too much activities for some reason, except what we have been proposing, observed with the UVIT, and there are no other proposals, and I don't understand why it is so. But anyway, let me tell you what from distant shift to nearby objects. Planetary nebulae is one of the early, these things, how do you do? How do you move this? Oh, yes. Let me tell you what planetary nebulae are to remind you. William Herschel, in 1790, noticed that little patch of nebula around it and got it shining fluid, a most singular phenomena. That is the phenomena which we would like to explore and do in the ultraviolet mostly. Stars, planetary nebulae are a remnants of a glorious death of intermediate mass stars. Can you hear me all right? Intermediate mass stars between, say, 1 and 8 solar masses or so. They take the path, for example, from here and become red giants and then become AGB stars. AGB star is where the energy is provided by two shells, nuclear burning shells. One is deep helium and the other is hydrogen. And the star is huge, that the mass loss is enormous there. Most of the mass of the star is lost in this phase by dust-driven winds or pulsations. And as the mass is lost, and to an extent, most of the envelope is taken away, and the nuclear burning subsides with the hydrogen. The source of energy is stopped, so then the core starts contracting. And whereas the outer envelope, which is shed as a very low velocity envelope, which is expanding, the core contracts into a kind of white dwarf. And this contraction makes, as it heats it up and produces ultraviolet radiation. Once it exceeds 30,000 degrees temperature or so, and ionizes the gas which is ejected earlier. So that's what glows, and that's what is nebula, planetary nebulae. It's its own. And planetary nebulae are important mainly because it brings out the interior or the nucleosynthetic material and spills it out into interstellar medium. To understand them, the chemical composition, to understand the morphology is very important for both mass loss as well as for the enriching the interstellar medium. And normal typical picture is that you have a expanding cool gas shell and pumped up by the hot central star. And this central star also produces, as it gets hotter, a hot wind. This wind goes and interacts with the outer envelope of it, generates a shock, and shapes the whole planetary nebulae. That's typical, picture. But of course, reality is not that. It's modified by so many other factors: magnetic fields, sporadic ejections, random these things. So you see varieties of shapes in the planetary nebulae. So, and most importantly, a companion can wholly change the shape and so on. But you still have to understand the ionization structure and how the temperature, so that you can estimate the abundances of stuff from the lighting emissions. Planetary nebulae mostly are emission line objects. The continuum and the nebula itself is fairly big. So what you are observing is in this mostly through various displays. That's already written there. UV is very important mainly because it has very important lines in the ultraviolet. As you can see, carbon, for example, in the optical region, the lines of carbon are few. If you want to get carbon abundance in the nebula, you have to go to the ultraviolet. And that also occurs in different stages of ionization. So you can also sample the ionization structure. So there are carbon 2 here, 2297, there's a 2326, carbon 4 here, carbon 3 there. So you have an ionization sampling of, if you can image them in these lines. Some of our filters in UV IT have been chosen with this view in mind, so that we can image the three-dimensional or two-dimensional structure of in the various ionization stages to understand the well, of course, this is the UV and various filters, which I think what we are going to image is all in spectral lines, emission lines, not the, and the important lines in the for UV, for example, occurs in this region, carbon 4 and carbon 2. Let me show you a spectrum which various designations of the line. For example, if you look at the high excitation planetary nebulae, these filters for top is the low excitation. There are not hardly any emission lines, the carbon 2, oxygen 1, and that comes in the F154W or something. I'm skipping. What happened to that? Can it go back? No. No. For example, this is one of the planetary nebulae, high excitation planetary nebulae. Most important lines like carbon 4 and helium 2 occur in this filter. Whereas that filter, which is 172M, hardly samples any filter. So you can differentiate what comes from the continuum and what comes from the, and these are high excitation lines, which are sampled temperatures around 10 to the 4, several times 10 to the 4, and so on. So you can build up a, sorry, I'm getting dry. Can I have some water, please? This gives you an example of what, so that's, and also luckily, one of these filters can also sample hydrogen molecule, which molecular Warner and Lyman bands occur shortward of 1608. So the filter, which is, for example, 169, yeah, samples hydrogen molecule if it exists. And the longward of that, we have a filter, which is, the contrast you can see. This samples the cool, very cool gas. At the same time, you have a facility to observe the ionized hot gas. And if, for example, in the reflection nebulae, there the gas is very cool. The ionizing photons from the star, which is far away, just comes and kicks it and then pumps it up, fluorescence, pumps it up to the upper level, it just cascades back. Which this is a kind of sampling that I say 63. So this is what you expect when you are imaging to in the various filters. Now let me go and tell you what we observed in the, well, this is an example of the simulation of that. Oh, okay. This is one of the first objects which we observed at the planet, at UVIT, in various filters. That is, we wanted to see how this highly ionized carbon-4 and helium-2 regions coincide with the X-ray. This is also an X-ray source. How is the diffuse X-ray spread along with this to sample the thermal gradient in the nebula? That was the idea about which we observed. And when we did this is a filter in the that is the HR. There is a filter in the 172 nanometers. That is there. This is the same nebular size as the optical. And when we observed in the 169, where it's supposed to be carbon-4 and helium-2, very highly ionized gas, which we expect to see, it's a much bigger halo than, much bigger, fainter halo than just the optical side. So this was a great surprise. You don't expect to see such gas, and which is, and when you look at the other ionized lines, there is no such image. This image is same as the core. So this, where does this come from? This emission in this filter. And that's where we've speculated that it could be because of the hydrogen molecular gas, which the star is hot enough to give you enough photons, ionized, high energy photons, to kick them up, and then they cascade back to fluorescent and give you that. And this is another major planetary nebula called Butterfly Nebula, which has been, I think, one of the best observed object in the sky in planetary nebulae, with all the known telescope, HST, with molecular, these things, everything. And we have observed the same object. This is optical size of the nebula here, down below in the H alpha. And this is UV80 filters. Most of the filters have roughly the same size or smaller because of the line emission is confined only to that little place. And this is a Oh boy. Really? Why can't I go back? Something is happening. Oh, okay. And most of them are very similar to optical, and it's a known kind of phenomenon. This is a butterfly, two big optical lobes on the sides, and it's bisected by a kind of vest, dark vest, which is a kind of disk which is around the central star. This is the star is completely covered by the dust and the cool gas. Whereas in this particular filter, again we see the extension going way outside to the almost to that extent, it's about twice the actual size, about 7 minutes of work on this side. In addition, there are few jets which were seen. This is again a new, unexpected presence. And again, this is not the part where the ionized emission is seen in the other lines, other species. So again, where does this emission coming from? No, I'm getting going, sorry to mess it up. Yeah, that's, here the emission is shown in the dark. The optical thing is the green part there, and the black, this thing is the lobes which are very extended. This is in the same direction as the optical lobes. And this has been very complemented, actually the later work, later after our realizing that there are jets and extra lobes around these stars in the same plane as the optical lobes. And there was a lot of work with HST imagery and various filters and so on. And Kastner and others, they actually complemented or compared our image to that. And this coincides with the jets up there, and this is an extension of the optical part. And then what we thought, because it's extended in cool gas outside, this must have been early ejections compared to the later part. See, the ages have been estimated for a central to around 5,000 to 7,000 years of the formation of the central. Whereas this, if you had to take the same expansion velocity as the rest of the gas and the product, it is much, much earlier. That is much older gas. That's what we thought in the first. And second thing was that this must be could even be the part of the AGB stage. And the structure of jets and this disk, big elongated disk, is a typical kind of produced in binary systems. There was already a model which has been bipolar nebulae are a result of interactions of binary stars rather than, and these jets and etc. are results of that, gas pumping out of the disk and perpendicular to that. And there's a lot more detailed modeling work then. And the detailed work also says that it's a sporadic, the kind of explosion at certain time around 1500 a year, 2000 years ago, and then the gas is thrown away through the lobes, and then there was an optical work which has been done with the long slit to see the velocity fields, and they show this flow along these lobes in certain parts is like Hubble's flow, that is, with respect to the distance, the velocity increases. And the outer parts of that, which reaches around 600 kilometers a second, that means a very fast motion. And Kastner and others say that these dark lobes which were seen in the carbon the filter F69 could be actually not the older one, the recent one with a high velocity. So they reached much further because of high velocity following the Hubble flow. But that has to be yet to be established. Only spectroscopy can do that. Now, whether this kind of phenomena exists in all the rest of the bipolar planetary nebulae is a question which we wanted to attempt. And that's where we observed one more object, which is I'm getting confused here. Which yesterday, Annapurni has already shown you this star nebula in a cluster, galactic cluster. Now, normally one can know what is the initial mass of the star, which is ultimately turning out to be central star of planetary nebulae and decaying, cooling down to a white dwarf stage. So white dwarf you can modulate by evolutionary tracks, but the initial mass from which it started is still unknown. It's a kind of guess most of the time from the evolutionary tracks. If you have an independent way of estimating that, the galactic clusters, then that's more direct evidence and gives you the authenticity for your. So luckily, there are few planetary nebulae associated with galactic clusters. Till recently, there were only 2 known, and now I think the number has increased to 4. But this is one of the very early combinations of galactic cluster associated with the planetary nebulae. And incidentally, this is also the same. Oh, sorry, finished? Just a few minutes. It's also the same object which was observed first with VBT, and we published a paper. Our group, which has Sharmila Arani and Annapurni, Pandey and others, we observed through UV18 ultraviolet, and luckily complemented by the Gaia proper motions and what the membership. Until recently, the membership of this, whether the planetary nebulae belongs to the cluster, is a big question. And luckily, our study of proper motions as well as radial velocities, which is complemented by other observers, say that it is a member. We could show that it's a member because the nebula and the cluster move with the same space velocity, and they're roughly at the same distance. And then, of course, these are the age is estimated of the cluster from the isochrones and so on. Since I don't have that much time, I'll rush it. Okay, the central star temperature is estimated from the UV-HE photometry as well as optical. It will be a very hot star, like some 190,000 K, 1,000 degrees temperature. And the track shows the, this shows that the final mass, the final mass, the initial mass from the cluster, this thing is about 2.1, and the present mass is about 66. Very recently, there was another paper which has done roughly the similar work, where they've drawn independent estimates of the nebular velocity and so on. They also conclude that both are associated. But there is a difference in estimated temperature as well as the initial mass slightly. But that is the thing which is to be resolved yet, unless more advances. Now let me show you a few things about nebula, which is very interesting. Oh boy. Why does this do that? Keeps going backwards. This is the planetary nebula in detail and this anyway you have seen. Now let me show you something else. Well, okay, the thing of interest here is the patches of small wisps of nebulosity there, here, which were seen in this filter of 154 only, not in the galaxy images, nor in other filters. So I was very suspicious. What is this? This is the proper nebula here. And these arcs, faint ones though, they do exist. The reality is quite, not beyond doubt, but quite very, very much there. What happened was very recently, another group they imaged this whole area in oxygen 3 line from the ground, giving an exposure of 8.6 hours. It's a huge amount of exposure. And they saw here a small wisp up there, exactly the same place where we saw it. Then what they did was they removed all the stars and rebuilt that patch there. See, the same emission which is seen there in carbon-4 and helium-2 is seen in oxygen-3 lines. So what we have seen very faintly and confirmed in this thing is now confirmed. Not only that, it showed a big nebulous structure up here. How do we understand this? This is it's a total mystery. Well, I will leave you at that since my time is over.
This is a crazy question. We know that ionization fronts cause star formation. In a similar fashion, your ionization front in the gas ejected,
Yes.
is there any evidence from ALMA and other observations of formation of cometary globules?
Yeah, well, globules are seen, yes, in planetary nebulae. Yeah, they are. That's it.
Okay, let's thank the speaker for a very nice talk, new images, and so on. So, next speaker, Manonita Chakravarti from IIT Indore. She'll be talking about probing neutron star low mass X-ray binaries with AstroSat. So she was at TFR at some stage and now in IIT Indore.
Yeah, am I audible? Yeah. So good morning, everyone. So first I would like to thank the organizers for giving me an opportunity to talk here, especially on neutron star low mass X-ray binaries, which is very close to my heart. So I'll be only giving a little bit glimpse of the exciting results from AstroSat, and obviously it will not be a comprehensive summary. That is a disclaimer that I like to give. I don't need to give an introduction of neutron stars because that has been very nicely done by Andrea. all I want to say is that they show a lot of interesting observational features which are very helpful towards answering various science questions. Primarily, again as mentioned by Andrea, the inner core of the neutron stars, what is the nature of the supranuclear degenerate matter inside it, which remains a burning question still now. And there have been various equation of state that has been proposed, and in order to constrain these equations of state, we need to measure the mass and radius with at least 10% precision, and that remains a kind of an open challenge. Furthermore, as you can see here, where we have shown the curvature as a function of the gravitational potential, the neutron star X-ray binaries occupy a top left corner of this diagram, meaning that gravity around this object reaches the strong field regime, giving us a unique opportunity to test all the theories of gravity in a strong field regime. Aside from that, this low mass X-ray binaries, again it has been mentioned in some of the talks, shows a transition between pulsars, and this is also giving us a unique opportunity to do population studies of the neutron star pulsar populations. And finally, obviously accretion physics around this neutron star binaries remains a lot of questions of a lot of interest. So just to introduce, neutron star low mass X-ray binaries during the outburst shows in their luminosity temperature diagram distinct tracks based on how their temperature, luminosity and spectral and temporal behavior evolves. And on this basis of that, they can be classified into two distinct states. One is this atolls and as shown in the A and B panels, and the Z's shown in the C panel. So depending on what particular branch of this atolls and Z's the neutron star LMXB are, the temporal and spectral behavior or the observational features that we see are very, very strong functions of that, and that can help us probe the accretion dynamics. Many question remains related to this transitions or this particular spectral states. Firstly, what drives the neutron star LMXB along these tracks? Secondly, how the geometry and the dynamics of the corona and the accretion disk and the boundary layer changes as the source moves along these tracks. And lastly, of course, how we have seen the atolls transitioning in the Z's and so forth. So the question is that what differs these two classes of binary systems, and how does the transition between these two are driven? So another particular interesting feature that we see from neutron star low mass X-ray binaries are the thermonuclear X-ray burst. This happens when the neutron star accretes matter from the companion, which gets accumulated on the surface of the star, builds up an accretion column, and the temperature and the pressure at the base of the column reaches certain favorable conditions, such a strong thermonuclear reaction is initiated. And this results in a strong increase in luminosity by at least an order of magnitude and a slow decay. The advantage of this is because these features happen on the surface of the neutron star, this gives one of the most promising tool to constrain the neutron star radius. As you can see from a good spectroscopy, we can get the radius of the neutron star. However, there is a lot of systematics that is involved that needs to be understood in order to constrain the radius in a reasonably accurate manner. Furthermore, as this flame spreads on the surface of the neutron star, a lot of exotic physics related to nuclear physics, as well as the astrophysical fluid dynamics that happens on the surface of the neutron star in this exotic scenario offers us a rich laboratory. And lastly, as the burning starts at a point on the surface of the neutron star, certain anisotropy emission is observed from the surface of the neutron star, resulting in a periodic oscillation. This oscillation can be used to probe how the flame spreads on the surface of the neutron star, as well as to measure the spin of the neutron star. The interesting thing is that to measure the radius of the neutron star using burst, the primary model to model the emission from the burst was a simple Planckian spectrum as shown by here, just an evolving Planckian spectrum. However, with more and more sensitive observations, what we see is that this is the spectrum is deviating from the Planckian nature, and there is a soft excess that is seen. This is primarily coming from due to the interaction of the burst photons with the corona or the accretion disk. Another possibility might be that the burst photons are imparting a radiation drag on the accretion flow, thereby hindering or enhancing the flow and resulting in a misinterpretation of the burst spectrum. This needs to be understood in order to estimate the mass radius of the neutron star. So just a quick statistics of the results of neutron star low mass extra binary using AstroSat. AstroSat have observed a number of low mass, different kind of low mass extra binaries, transients, radio bright sources, ultra compact extra binaries, deepers, and so, oops, I'm sorry. And also a fraction of bursters and non-bursters. In terms of spectral classes, the majority has been atolls, but there are a few Z sources as well as the transitional Z and atoll classes. This is the statistics of the publications. I will not dwell much on it, but these are the source-wise and year-wise publications. But let's come to the results. Firstly, the thermonuclear burst. AstroSat detected a triplet thermonuclear burst with a small separation of 5.5 minutes. This is extremely interesting because such a small separation basically means there is a lot of unspent fuel which is undergoing a rapid reignition after the formation of a original burst. Also, AstroSat has shown a burst in rapid succession from the flaring states of the Z sources, which is typically at higher accretion rate. And a burst at different accretion rates helps us to probe the different kind of ignition regimes. For example, at higher accretion, probably it's more helium-dominated burst, whereas at relatively lower accretion, it's mixed hydrogen and helium burst. So that has been shown. Moreover, a couple of bursts from AstroSat has shown oscillations, and this oscillation could be used to estimate the spin of the neutron star. However, there are still some very interesting ambiguities remains which remains to be answered. But interestingly enough, AstroSat has multiple instruments which give us opportunity to do a broadband spectroscopy of thermonuclear bursts, and this is precisely what we did. We looked at the spectrum of the thermonuclear burst using both SXT and LAC species. And this broadband spectroscopy helped us to determine this soft excess with a very, very strong evidence. And also, we could shed a little bit light on the actual nature, not just the detection, but actual nature of the soft excess. And also, it was seen that this nature of this additional component that is present there is showing a very strong correlation with the incoming seed photon flux. Basically means the more the photons are coming from the burst seed photons, the interaction with the surrounding environment is significantly increasing. And in one of the bursts, I'm sorry, this pointer is a little bit. So in one of the bursts, what we saw is that there was a hard X-ray dip seen at the peak of the burst, which is basically coming from the cooling of the corona through Comptonization of the seed photons that is coming from the burst seed photons. So that gives us strong evidence of burst surrounding interaction. And moreover, what we saw is that if we look at this burst without this soft excess and with this soft excess, there is a significant misrepresentation of the burst parameters, the temperature, the radius, when we are not taking into account the presence of this X-ray emission. So particularly for constraining this equation of state, therefore, this excess emission needs to be considered, and therefore, a broadband spectroscopy like that shown with AstroSat might be very, very relevant. Also, another interesting thing is that AstroSat has UVIT also, and we were lucky enough to see at least one burst with all three instruments, LAC-SPC, SXT, and UVIT. And the UV emission of the burst comes from the reprocessed of the burst seed photons from the accretion disk. And this gives a unique opportunity to map the accretion disk using a kind of a Doppler tomographic method. However, in this particular case, we were unfortunate to not get the full coverage of the UV burst, and only partial coverage was possible. So that means that the lag estimates couldn't be done, but in future such studies will give us a unique handle to understand how the accretion disk is flaring up, or if there is any undulation that is there on the accretion disk due to some instabilities. Interestingly enough, in one of the recent bursts we saw, particularly in the soft X-rays, after the peak of the burst, about 30 seconds after the peak of the burst, there was a secondary hump or a secondary peak. This hump is very interesting because this has been reported in earlier bursts, but in this particular case what we saw is that the hump corresponded to not an increase in temperature but an increase in radius. What gives rise to the hump? It's still not fully explained, but it may be possible that there is some sort of a secondary reignition of the unburned fuel that is happening, or there is a stalling of the flame due to some confinement, either due to magnetic field or due to some Coriolis force effect, and then sudden release of that stalling that is happening. It may be also possible that there is some nuclear physics reactions are ongoing. There have been some models that is proposed. However, the time scales are still not consistent with the kind of time scales that we are looking at. Ranjiv mentioned that it would be very interesting to look at AstroSat along with other instruments like NICER. So we were lucky enough to look at some bursts with NICER which had simultaneous observations with AstroSat. Again, this gave us a broadband spectroscopic coverage, and with that what we saw is that the excess emission that is there in the burst due to the burst accretion interaction could be actually traced over longer times when the broadband coverage is present, even for the relatively fainter bursts. So you see NICER and NICER plus lag species. So NICER plus lag species gave us a coverage of the red point show the effect of the burst accretion interaction, and we could actually efficiently track the burst accretion interaction over longer durations. Also, NICER plus lag species gave us a better, the estimates were the same, but the precision of those measurements of the temperature and the radius of the burst emission was much better constrained when both NICER and lag species was present together. So that was pretty interesting, particularly in the context of constraining the radius. I come to a slightly different feature which is called kilohertz quasi-periodic oscillations. These are basically periodic oscillations that are seen from neutron star low mass X-ray binaries in the kilohertz range, and as you can see one such example here. Here they are happening around 800 to thousands of hertz, and they typically happen in a twine manner together. And there was a low frequency quasi-periodic oscillation which was also observed along with this. This origin of this quasi-periodic oscillation is still debated. That the main idea is that they are possibly coming from the relativistic precision model, and this frequency basically represents the spin frequency, the periastron precision frequency, and the nodal frequency around the neutron star accretion flow. The good thing is that what was observed is that, not we, but what was observed that the low frequency and the upper kilohertz QPO frequency correlation shows a correlation which is precisely consistent with the relativistic precision model, giving an insight onto the origin, and they are very, very good tools for constraining the ISCO, the innermost stable circular orbit. And in this case, using this constraint on the ISCO, measurement of the neutron, a constraint on the neutron star equation of state could also be given, which indicated towards a stiffer equation of state. But the more important thing I want to focus on is that this kilohertz quasi-periodic oscillation also showed a variation. The frequency showed a dynamic evolution of a few hertz. And as the QPO frequency evolved, first of all, the spectra of the QPO was consistent with the increase with the energy, which basically means that the Comptonizing corona is a key contributor to the QPO emission, first of all. Secondly, the changes in the QPO were driven by the heating of the corona. But because I talked about burst, I want to connect it to that idea. And what was interesting is the burst and the kilohertz QPO actually are showing connections. For example, when this QPO frequency increase, when this QPO frequency increase was happening, at the point where the QPO frequency reached the maximum, it coincided with the occurrence of a thermonuclear burst. But more interestingly, here in this particular example, there was a QPO prior to the occurrence of a thermonuclear burst. As the thermonuclear burst happened, the QPO vanished for about 200 seconds, and then the QPO reappeared again. In Professor Singh's talk, we heard about a novae disrupting the inner accretion flow. This is kind of probably a similar scenario happening here, analogous scenario happening here, where the occurrence of a thermonuclear burst disrupted the inner accretion disk flow, and then the reformation of the disk happened, which resulted in the reappearance of the QPO. This is a very interesting result which gives a connection of the QPO and the burst. And the last part, I want to focus on the evolution of the state of the neutron star low mass X-ray binaries. I mentioned the atoll sources. So for the atoll sources, the broadband coverage of the AstroSat using both SXT and LAX-PC gave us a handle to model the spectra. And what could be seen that as the source, particularly for the Fenter sources, as the source goes softer, there is initially there was a truncated cool accretion disk which was sitting outside, and as the source goes softer, this disk comes inwards, gets hotter, and results in the change in the spectral state, which is also seen in some other examples as the source goes along with the banana curve. More importantly, there is also a change in the coronal emission as the source goes towards the harder and softer states by resulting in the increase in the coronal optical depth. We also looked at the Z sources, and AstroSat shows that the Z tracks are significantly driven by changes in both the boundary layer as well as the coronal quantizing contribution. There were oscillations that were observed in all three branches of the Z track, the near branch oscillations, the horizontal branch oscillations, and the flaring branch oscillations, each representing different origin mechanisms. In particular, we focused on this particular source where there was a very variable state and there was a relatively quieter state. The variable state corresponds to the flaring branch, whereas the relatively quieter state represents the near branch. And in both states, we observe this oscillations or peaked nature. The idea is that this, as the source is going from the near branch to the flaring branch, there is a heating of the boundary layer that is happening, which is driving the source in this variable flaring branch state. And this near flaring branch oscillation is possibly coming from the shock that is happening in the inner accretion flow as the boundary layer is getting heated up. And the near branch oscillations, whereas as opposed to it, is coming from the transition layer between the accretion disk and the boundary layer in the inner accretion flow. So this gives an insight on how this is happening. Just to summarize, therefore, the results on neutron star LMXBs give us a lot of insight on how burst interacts with its surroundings. However, there remains a lot of questions on the exact nature of this interaction. Is it really reflection or is it the Ponting-Robertson drag? And how this burst is connected to the kilohertz quasi-periodic oscillations that we see. There also are questions on how this QPO is related to the neutron star, let's say, innermost stable circular orbit and the magnetospheric, the Alfvén radius. There are a lot of interesting calculations and estimates that AstroSat results have given from the QPO on the magnetic dipole moment of the neutron star or on the neutron star mass radius. But further insights are required. And finally, the evolution along the Z and atoll tracks are shown by how this component evolves, but detailed broadband spectroscopic modeling is required for understanding how this corona and accretion and boundary layer geometry is changing with the states. And finally, this calls for AstroSat-like instruments with broadband coverage, like others have pointed out, with high energy sensitivity, a large effective area at high energies to further further answer the questions raised by AstroSat related to the science related to the neutron star LMXVs. Thank you.
Thank you.
Manonita, nice talk. You talked about the spectrum with the black body, and you also showed that there is a softer emission component. So I have missed possibly what could be the origin of the softer emission?
Yeah, so there are a couple of possibilities. One is the burst is interacting with either the corona or the accretion disk, and thereby modulating its original, thermal emission. So finally, what you are seeing is burst plus the modulated emission. So when you try to model it with a single black body, the excess is reflecting the interaction part.
In that case, what would be the reprocessing? Because you don't have any disk contribution, I see.
The disk contributions were subtracted out.
Okay. Oh, it's subtracted out.
Yeah.
Okay. Okay. Thank you.
Hi, Maranita. Excellent summary of the whole neutron star work done by AstroSat. I have one question on the light curve you shown for this 30 to 80 keV where you seen the diff during this type 1 burst. Have you seen that in all type 1 burst or one?
Okay, that's a very interesting question. So it is not present in all bursts. So the idea is consistent with where you expect the corona to be, because this cooling is happening from the corona. So in certain states, if the corona is not that dominant, you won't expect that much cooling and that deep to be present always.
Okay,
and that kind of state evolution has been seen.
Okay, have you checked the background in 30 to 80 keV, because 30 to 80 keV is supposed to be dominated by background a lot, and you have seen a dip in your light curve, which means, I don't know, just.
Yeah, we have done the background correction, and even after that, this significant dip was present. And in some later cases, we have also tested the effects of dead time and all those kind of contributions.
Manita, my question is regarding these bursts that happen in quick succession, like the triple burst that you showed. So what causes, is there any understanding of what causes certain amount of fuel to remain unspent? And once the fuel is depleted, how is the ignition condition made again and again, in this case twice in rapid succession?
Yeah, that's actually I think unanswered question till now, but couple of possibilities I can suggest. One is there is some heating, history from the previous burst that is remaining, that is helping, some of the, if the accretion rate is high enough, helping some of the new fresher fuel to ignite in a more easier manner compared to the previous burst. That's one possibility. The other possibility is there is some confinement of the fuel that is happening, either due to some magnetic field, dynamical magnetic field, or due to some Coriolis force induced effect. And the confinement is, increasing the local ignition conditions, enhancing the local ignition conditions, resulting in this kind of secondary burning. Obviously, this needs to be tested further to understand which condition can be more probable.
The fact that the QPO precedes the burst, does that in any way constrain the kind of instabilities that give rise to the QPO itself? And could it possibly have any connection with the secondary bursts?
Secondary bursts, okay, I can answer in this way. The QPO instability would be related to the accretion rate, and the accretion rate will also kind of affect this occurrence of the secondary burst. So in that way, those two might be connected. However, the precise QPO instability, whether it will affect the secondary burst, I am not sure about that fact. Yes.
Okay. So in some of the bursts, we do see burst oscillations.
Right.
Or many are not, do not show oscillations. So if oscillations is seen, then it's obvious that you can detect pulsation, right? Pulsation.
Oscillation. Yeah.
Pulsation, right?
Oscillation.
So where there is no pulse, burst oscillation, but still you do see thermal burst, how do you get pulsation in those bursts?
Sorry, I didn't fully understand
So
the
even
question.
if bursts do not showing burst oscillation, still you do see pulsations during burst, right?
No, the oscillation during burst is called burst oscillation.
Yes. So burst oscillation is not there,
Okay.
but still you do see neutron star pulsation.
Okay. Oh, so for the cases where the neutron star is also a pulsar, yes, definitely during the burst we see pulsations. However, in that case the pulsation is kind of the same level of the pulsation that is present during the non-burst phase. So you basically compare the pulse amplitude during the burst and prior to the burst, and that will kind of tell you whether the contribution is coming only from the pulsation or the pulsation plus something else, some additional anisotropy is ongoing.
Okay, last question.
Yeah, Manolita, just to add, a very nice talk, by the way. So when you mentioned about the dip across the peak of the burst, actually we also investigated, and in fact in one of our bursts we also observed that dip, but once the accurately dead time correction was done, that dip disappeared. So we cast doubt about the dip behavior in the hard X-ray band, because with integral people have reported that in the hard X-ray, and that plausibility of the cooling of the corona, etc., has been explained. But with AstroSat, we had few apprehensions, and we did not really made a strong claim that there's cooling of this corona. In our paper, actually, we did mention that.
Interesting point, and I kind of agree with that. In one of our recent bursts, the one I didn't show, we see actually that happening, that the dip was apparently present there, and when we saw that actually did the dead time correction, energy dependent dead time correction, it took away the actual significance of the dip. Yeah, that may be a factor, but I think the case that I showed, in that case the dip was significant enough to for the dead time not to take away the full significance out of the presence of the dip.
Okay, let's thank the speaker for a very exciting talk, and for everyone for a good question hour. So, moving on to the next talk, the last talk of this session, by Santa Brata Das. He'll be talking about spectral temporal studies of black hole X-ray binaries with AstroSat. Santa Brata from IIT Guwahati. And he has been holding a lot of such workshops even before the launch of AstroSat and then beyond, and teaching people how to do study binaries and so on.
Hello, am I audible? First of all, I'm really grateful to get this platform in talking about the black hole X-ray binaries. Thanks the organizer for giving me this platform. I'll talk about spectrotemporal studies of black hole X-ray binaries with AstroSat. These are my collaborators in this work. Partly I will cover. AstroSat is a fantastic instrument, and it doesn't require any further clarification why it is so, particularly in studying the variability properties in X-rays. The lag species is giving a fantastic effective area. To talk about the black hole X-ray binaries, the first light of black hole X-ray binaries that were captured just after launch of the AstroSat is GRS 1915-105. And thereafter, altogether, 34 black hole X-ray binaries are detected by the AstroSats, and more than 70 publications happened till today. I'm not very sure about the numbers. There might be some slips, but it is of the order of. Altogether, we analyzed 12 megasecond exposure time involving all these 34 black hole X-ray binaries. The major fraction goes to Cygnus X1 and GRS 1915-105. And this is the pie chart giving the relative ratios of exposure time. Altogether, out of 12 megasecond exposure, this pie chart contains sources which have exposure time something about 1.5% or so, and which is less. They are listed here. This is the galactic coordinate positions of all these black hole X-ray binary sources. Some of the sources are out of the galactic plane. Now, based on the long-term X-ray variabilities, broadly we can classify all these 34 black hole XRBs in 3 different classes. One is the persistent source, something about Cygnus X1, Cygnus X3, LMC X1 and so on. And then outbursting sources, occasional X-ray flaring you can expect. And there is a peculiar behavior, at least in a couple of sources, this aperiodic persistent sources, to be very precise, something like GRS 15105. Now, altogether, these are the table contains 3 persistent variable sources, 5 persistent sources, and 26 transient sources. For the interest of time, I can't cover all of them together, but at least I will try to show you the glimpses of each categories. To start with, it's undoubtedly a very enigmatic source, GRS 1515105. It's persistently showed bright variably. It remains bright and variable over more than 30 years or so since its discovery in 1992. And presently it appears to be a dead star. It is massive, something about 12.4 solar mass. It's highly spinning and it's galactic source. It exhibits a remarkably broad range of peculiar and repetitive time variabilities in the scale of second to minute, if not more. And it has a fantastic spectrotemporal variability that can give us some clue to understand what kind of plasma dynamics is happening around it. So the first result of AstroSat towards the black hole X-ray binaries comes through the Chi class observations by Jadhav sir. I don't see him here, but he must be somewhere here. And in this paper, it was mentioned that the energy-dependent low-frequency QPO, time lag variabilities, spectrotemporal properties, and everything. Thereafter, there are multiple observations by the AstroSat for black hole X-ray binary sources. Altogether, 9 distinct variability classes was identified by various groups of people. In these plots, I show the distinct variability classes, 9 distinct variability classes with increasing time span, starting from theta class to chi class via different classes. In each panel, you can see the lag species counts along with the SXT, and this gives you the CCD diagram. Very recently, we found one new variability classes. It is basically, we named it as a tau class. It's a combination of, it has some combination very common to the rho class and some combination is very common to the delta class. It's something like a transition between these 2 classes. So altogether, considering all these 9 variability classes, some of the classes distinctly show the low frequency quasi-periodic oscillations in the range from 1.38 to 7.55 Hertz. And in some variability classes, distinctly show high frequency QPOs. So in these discussions, I will talk about something related to the high frequency QPO. More finer details will be talked by Brojo, I think, this afternoon for low frequency QPOs. I encourage you to attend if you are interested. In a very recent analysis, we observed, we comprehensively analyzed AstroSat data for 4 different classes from delta, kappa, omega, and gamma. And these are the software relativity classes, and we identified high frequency QPOs. And these high frequency QPOs are remarkably energy dependent. Only in the 6 to 25 kV, the high frequency QPO features are available, but in other energy bands, it's not available. What is remarkable in this work, you see, the omega class variations, it has a distinct features of dips and non-dips. If you look at the power density spectra in the dips phase, the QPO features are absolutely not present. Only in the non-dips phase, the QPO features are present. And these differences are happening within 100 seconds or so. What is the reason behind it is very, very difficult to understand, but these features are further analyzed in terms of the time evolution of the power density spectra, and you can see that when there is a non-diff, you can see excess power around 70 Hertz, and when these excess powers are happening, the inner disk radius becomes very small. So that means if it is coming from the corona becomes extremely compact. And when these QPO features are disappear, this effective emission region becomes larger. And it also follows the luminosity behavior. Okay. Then we carried out the similar analysis for all other software variability classes, and high frequency QPOs are observed there. Remarkably, we find possibly the first time the twin high frequency quasi-periodic oscillations, something about 152 Hertz or so. We also studied the time lag in high frequency QPOs. I think this afternoon Prajwal will talk about it in more details. And for at least two different classes, low Hertz state and high soft state, relatively softer state, we studied the spectral properties, and it is a kind of common consensus that the high emission components are coming from the corona, and the softer part is contributed due to the Keplerian flow. We also carried out analysis for Cygnus X1, particularly the very softest state was identified where I think a couple of years ago by Ankur and his team. And similar observations we have done for Cygnus X3. I think Mayuk has got some quasi-periodic oscillations in Cygnus X3. We got a little bit higher frequency compared to that, but it also shows the spectral variabilities for these sources. To move on, I'll talk about the persistent sources, particularly for 4U1957 and 115. I chose this source particularly because we found a quasi-periodic oscillation, A-type quasi-periodic oscillation for this source in the frequency range of something like 2.66 or so. It has a high Q factor and reasonably good significance. And it also comes with a very weak harmonic features. Depending on its covering fraction values, it is predicted that possibly the disk is highly dominated by the soft emissions. Now, this source is discovered very recently in 2023. And in this source, we identified the evolving quasi-periodic oscillation features starting from 1.09 to 2.66. And at the same time, we also identified the energy varied quasi-periodic oscillations which exceeds 80 keV. For this source, I think Gulab groups also calculated the mass, spin, and distance of this, and I think it agrees quite well with the spectropolarimetric observations. For the interest of time, I need to speed up for some other directions. Let's talk about the spectropolarimetric studies, particularly for the spectral correlations. If you see the correlations among the photon index as well as the relative component of disk flux, by and large, there is a common tendency that if the disk component increases, the spectrum becomes softens, and the color indicates the bolometric luminosity, and this also agrees quite well. Now, this is a kind of observations we did it for GRS 1915-105, and we extended this for another 17 sources. And we found that during the low Hertz state, the photon index roughly remains somewhat constant, and the bolometric luminosity roughly increases. But as the disk components is increasing, the spectral softening is by and large agrees with our common notions, with some exceptions are there, but anyway, the idea is to find out a grand unification so that all the black hole X-ray binaries can be fitted with a one understanding. Well, we extended it to spectrocorrelation temporation in terms of spectrotemporal correlation in terms of the photon index and the frequency. We find a nice correlations up to less than 10 Hertz or so, but after we found some saturations for GRS. And we extended this correlation study to other black hole sources. We found some correlations which is not very precise, but obviously there are some modest correlation is present here. We also carried out the time lag calculations for some of the high inclination black hole XRV sources, and apparently what we found that the type P QPO essentially exhibits the hard lag compared to the type C QPOs, which is mostly remains in the soft lag domain, particularly when the relative component, relative comptonization flux is weak. But when this relative comptonization flux is significantly high, then some sources do show the negative lag, some sources do show positive lags, although both all the sources essentially exhibit type C QPOs. For more details about this time lag analysis, I think Prajwal and Sitoma, they will going to talk this morning and tomorrow, this afternoon and tomorrow morning, so you can attend their talks. And thereafter, I mean, being a theorist, I can't resist myself to include some equations in the slides. The modest as well as some significant correlations between the spectral and timing parameters essentially indicates that there must be some underlying physics happening which are responsible for emitting those radiations. So if you want to understand those radiations, what you need to do it from the first principle, you have to solve set of equations that describing the accretion flow around the black holes. So these are the set of equations. Very recently, we were successful to identify effective potential that satisfactorily describe the black hole space-time. So idea is, this is the schematic diagram for black hole X-ray binary sources. This is the companion, this is the black holes. We focus only in this region, identified a disk along with a post-shock corona. And then we did a remarkable things in the sense that all those equations are time dependent. And solution of this time dependent equation is extremely challenging, not only in terms of complexity, in terms of computational time. So what we did, we calculated everything in the steady state, just dropping the time variations. The reason is, if you look at the viscous time scale in the inner part of the accretion disk, the viscous time scale is so large, the angular momentum transport usually doesn't happen. The flow enters into the black hole with angular momentum of the order of angular momentum at the marginally stable orbit. So in this region, the flow is expected to be radial in nature. So if I calculate the radial infall and subsequently calculate the time scale of the radial infall, so this is the way I can calculate the radial infall time scale. So this time scale can be calculated from the post-shock boundary to the inner radius, and if I know the post-shock velocities, I can calculate the time scale. Once I know the time scale, this can give you a measure of quasi-periodic oscillations. And subsequently, I can calculate the luminosity associated with these accretion flows. So we did these calculations from the shock accretion solutions. The boundary for the shock, I get it from here. This is the post-shock velocity. I inserted this information here and I calculate the quasi-periodic oscillations. I know the thermodynamical properties in terms of the density and the temperature. I also can calculate the luminosities, and this is the result. The wide range of luminosity and the QPO frequency can be calculated just by tuning the model parameters, just like accretion rate and viscosity or something like that. So with that, the steady state scenario can be understood. I encourage you to look at the talk by Cabelia. He extended this work in the magnetized situations. After that, I relaxed these conditions of time independency. I introduced time dependency and calculated the three distinct scenarios that GRS 1915105 exhibited. One is the very high frequency QPO, one is the very low frequency QPO, and no QPO. You look at this. This is the numerical simulation exhibiting the low frequency QPO. This is the high frequency QPO, very compact corona, and there is no QPO. Thereafter, I identified the boundary of this corona and see how the time evolution happens for these three scenarios. This is the boundary of the corona. this is the corresponding luminosities. You see that when there is no variation of the corona size is not changing, luminosity variation is not there. This is a very reasonable variations. It gives a low frequency QPO. The QPO frequency is very high and it gives a very strong oscillations. These we calculated in terms of the power series, and you see that the reasonable peaks are appeared. We are little bit uncertain about this features, which is anyway very low, but we are successful to reproduce some of the very high frequency QPOs near about 70 hertz. Well, with this, I move on to the spectral modeling using the solutions that we have. This work majorly led by Samir. A part of it Samir yesterday showed. 3 different distinct classes that I showed at the beginning for the GRS. We feed these 3 different classes. One is the hard state and 2 softer variability classes. And when we feed these 3 different classes with our model, hybrid 2-component accretion flow model, we got a very consistent parameter, which is the size of the corona. Particularly in the softer variability classes, the size of the corona is matching reasonably well with these softer variability classes. Okay. I'm sorry. Yeah, softer variability classes, it is matching reasonably well with this. We got some very high accretion rate for these 2 cases. These possibly the caveats in our models, because you know that any models is based on some fundamental assumptions, and those assumptions could be responsible for this. But this estimate is coming independently from the numerical simulations. Finally, the Dixit geometry. The motivation of the entire study is to identify a unified system which can explain any scenarios related to the black hole X-ray binaries, starting from timing and extended to the spectral properties. Be it a high frequency QPO, be it a low frequency QPO, be it a no QPO. So this is the proposed scenarios. At least 2 cases we are successful to reproduce from the simulations. In the low Hertz state, this is the features, radially extended corona. Keplerian disk will be truncated at very far away from the black hole. Spectra is dominated by the strong comptonized emissions, and thermal component will be very weak. Thereafter, the high intermediate states can be identified with the relatively prominent Keplerian disks. The comptonized emission is still present because corona is relatively smaller in size compared to the low Hertz state. The type C QPOs can be identified in low frequency domain, and this quasi-periodic oscillation possibly resulted because of the undulation of corona that I just showed in the simulation results. Then high soft intermediate states, the Keplerian component becomes more prominent, the disk emission is enhanced and steeper spectra, and the high soft state, possibly the source, the domain of high frequency QPOs. And for the persistent source, these 2 things can be interchanged. So with this, I stop here. Thank you for your attention.
Thank you for a very nice talk.
In GRS 1915, you showed class-dependent spectrum as well as occurrence QPO in classes. But each class is a variability in 3 states.
Yes.
Okay. A, B, C. So isn't it worthwhile to make this analysis for states in these classes rather than class-wise?
Yeah, that can be done. Yeah.
But that is much more meaningful, isn't it?
Yeah,
the
yeah,
whole variability class is only transition in 3 states. So most of the property is state dependent. Okay. So if you do the state-wise analysis within class, answer is that a state in particular different classes, do they behave identically? These might give some.
Yeah, that's a nice suggestion, I would say. I mean, the primary motivation of this work is to bring every observables, black hole, X-ray binary observables into the common umbrella. So we didn't go to that finer details.
In GRS, when you want to put the theory to explain the QPO, you can't average 3 states and make a
Yeah, I know these things because
So
the
you
reason,
have to do state-wise.
the reason is, as I said, these episodic quasi-periodic oscillations. In every 150 seconds, we do see quasi-periodic oscillation and then it disappears. We do not have any idea, any clue, scientific clue that which can really explain this dynamic behavior. Obviously, that is the role of viscosity as well as the accretion rate, but we need to figure it out exactly how it works. Yes, sir.
With regard to these coronal oscillations, what are the conjectures regarding the nature and the underlying physics of the oscillation itself?
Who is responsible for these oscillations?
Not who is responsible, but when you have an oscillation, something is happening, right? Something is oscillating. Some thermodynamic quantity is varying with time.
Okay.
So what is the conjecture of what is actually happening? Is it pressure oscillations or is it density oscillations?
Yeah, here, what exactly we do, we are injecting plasma at some radius, from some radius, let's say 100 gravitational radii, with some thermodynamical properties. Let's say it has this particular temperature, density, velocity, and everything. And then we just inject it in the domain of very extreme gravitating scenario. And depending on its thermodynamical properties, sometimes it do show oscillations, sometimes it doesn't show oscillations. The oscillation character can be very fast, slow. Now, yes, I'm coming to your questions. Everything is oscillating. Entire plasma is oscillating.
He's asking, is it density oscillation or pressure
No,
oscillation?
if plasma oscillates, plasma is a collection of particles.
Yes.
So when plasma oscillates, the entire particles embedded within this plasma is taking part in the oscillations. Its density, its velocity is also contributing, its temperature is also contributing, everything.
The reason I ask you, if it is plasma oscillation, conventional plasma oscillations are determined by the density of the plasma, right? The plasma frequency is defined as 4 pi Ne squared divided by m.
Well, so that features is relevant when you go to that length when the electron and ions are separated. These are neutral plasma. So you can treat them as a whole, that obviously the temperature is very high, which everything is in the state of plasma, but as a whole, collectively, we are not solving any Maxwell's equations to treat them. As a whole, we consider as a parcel of material, which are inherently plasma, but collectively they are not behaving like the separation of ions and electrons. Yeah.
Okay, let's thank Santa Pratap for a very nice talk. And thanks to all the speakers who have given talks today in the morning session.
We'll start the next session. This session will be chaired by Professor Dipankar Bhattacharya. He is a senior astrophysicist, previously at IUCA, now currently at Ashoka University. He is the present chair of the AstroSat Science Working Group and helping to defend or to prospect the mission science goals, how the operation should happen, what the unique science proposals we can consider. He also helped to design various design aspects of coded aperture marks and the pipeline of AstroSat overall softwares. And he has continuously contributing to the GRB science from AstroSat. I request Professor Dipankar to take over.
Thank you. We have 4 very exciting talks lined up in this session. So please take your seats. I would request you to put your mobile phones in the silent mode. Our first speaker is Sachindra Naik, who is from the Physical Research Laboratory, a well-known expert on high-mass X-ray binaries, and he has served as the secretary of the AstroSat Time Allocation Committee for quite a while. So, Sachi, please.
Okay, so let me thank the organizers for inviting me to speak on AstroSat observations of high-mass X-ray binary pulsars. So, yesterday and today we have already had 2 talks on accreting millisecond pulsars in low-mass X-ray binaries. So, low-mass X-ray binary means the companion is a low-mass star, mass compared to the mass of the sun, whereas the compact object is a neutron star. Whereas in case of high-mass X-ray binaries, the companion is a massive over B-type stars, and the compact object is a neutron star. Okay, so that's not the only difference. In AMXPs, because the mass of the component is very low, the accretion takes place through Rousseau overflow. That's a steady flow of matter onto the neutron star. In the process, forms accretion disk, and the magnetic field of these neutron stars is the order of 10 to the 7 to 10 to the 9 or 10 Gauss. Is basically low compared to the neutron stars in the high mass X-ray binaries. So because of this low magnetic field, the accretion disk can get extended closer to the surface of the neutron star, and matter can get accumulated on the surface, and after some time it goes into thermonuclear X-ray outburst, X-ray burst, which we have heard already from two talks. Yesterday Andrea spoke about it, and today Manonita also spoke about it. However, in case of high mass X-ray binary pulsars, the magnetic field of the neutron star is order of 10 to the 12 Gauss, about 2-3 orders of magnitude higher than the LMXPs, neutron star. So, because of this strong magnetic field, the accretion disk cannot approach the surface of the neutron star. So, and it gets truncated at a magnetospheric radius, which is far away. So then matter from this inner part of the accretion disk gets channeled by the magnetic field lines of forces, and finally falling on the poles of the neutron star, forming different processes, accretion column and other things. So that's the major difference in case of low mass X-ray binaries, accreting millisecond pulsars, and also high mass X-ray binary pulsars. So here, so I'll speak about mainly high mass X-ray binary pulsars. So in the beginning, I will briefly again explain about what are these objects and what's the emission mechanism in these systems, and then observations of high mass X-ray binary pulsars with AstroSat. So there are many observations, many papers have come out, but I picked few of them where I find interesting, and then I'll discuss about that. And then, so, hello, am I audible? Yeah. So that in these systems, I'll describe first timing properties, what kind of timing properties we observe. That's a pulse period measurements, pulse period evolution, cyclotron scattering features, and then I'll summarize the results. Okay. So as I said, high mass X-ray binary pulsar, the component is a massive star of more than 10 solar mass or so. So even if within the high mass X-ray binary systems, there are two different types of systems, like supergiant X-ray binaries, where the component is a supergiant ORB type supergiant star, and in these systems, basically the accretion happens because of capture of stellar wind. In these massive stars, high radiation pressure inside the star throws out matter from the companion into the space, part of which is accreted onto the neutron star, and you get X-rays from that. So in these kind of systems, this is the basically mass loss rate from these companion stars, supergiant stars. This period, orbital period, is in the order of 3 to 60 days, whereas the spin period of the neutron star in these systems is greater than or around 100 seconds. In these supergiant X-ray binaries, some are persistent, whereas some others are transients. Transient things means suddenly increasing the intensity by order of magnitude or more, and then after some time again coming back to persistent level. So another kind of high mass X-ray binary, B X-ray binaries. In this system, the component is a B star, rapidly rotating B star. Because of rapid rotation, the photospheric matter is equatorially spread out, forming a decreasing disk around the companion star, and the neutron star in the binary, while passing through the perihelion, captures a lot of mass from this disk, and that gives you X-ray enhancement in the X-ray emission from the neutron star. That we call as X-ray outburst. So in these kind of systems, basically orbital period is more than about 20 days, and then spin period is wide range in 1 to 1,000 seconds or so. So in these systems, B X-ray binaries, we do see two different kinds of outbursts. Basically, one is type 1, type 2, that is how we say, but the type 1 means that's basically in each orbit, while the perihelion passage of the neutron star, it captures matter and gives you X-ray enhancement. That is type 1. These outbursts are extremely periodic. Basically, one orbital period, you expect to see one outburst if the circumstellar disk is well evolved. Otherwise, we may not see this kind of outburst. But type 2 outbursts, when the intensity goes by 2-3 orders of magnitude more, that is extremely rare. And we don't know what's the cause of this kind of outbursts in these systems. Anyway, so these two are high mass X-ray binary systems. So then pictorially, if you see, this is supergiant X-ray, fast X-ray transient. This transient outburst here in this case is for a few tens of seconds. This is Bozo et al. Bozo is in the audience here. This is from his paper, his work. So basically how he explained this kind of outburst in the supergiant exobinaries, basically this is the neutron star, this is supergiant companion, so these are the stellar wind. So sometimes some huge amount of matter being released, and as long as it has not approached the neutron star, we will see quiescent. So when it approaches or reaches neutron star, the X-ray enhancement starts. And when it is completely consumed, and then coming back to normal state, then again you come back to the quiescent. So that's supergiant first X-ray outburst. Whereas in case of B X-ray binaries, this is the B star, this is the circumstantial disk because of rapid rotation of the star. And whenever neutron star approaches the perihelion, takes away matter, and then because of that, you will see X-ray enhancement. And once again it goes to in orbit, again when it approaches this disk, again you see X-ray enhancement. That is why it is expected to see regular outbursts in this kind of systems if the circumferential disk is well evolved. If it is not well evolved, then you may miss some of the outbursts at the perihelion passage, otherwise it is frequent. So this is these are two examples of this kind of systems. See, this is EXO 2030 process 375. Here exactly the disk is evolved, you can say, so that you see always after 40 or 41 days, it's the X-ray outburst. So each time it passes through perihelion, it gives you X-ray enhancement. These are type 1 outbursts. So, however, this kind of huge outbursts are seen sometimes which are rare once in decades or so when the intensity goes up rapidly by orders, 2 or 3 orders of magnitude. So, the origin of this kind of outbursts is now not well understood. Some people say because of accretion from the wrapped circumstantial disk or disk evaluation or something like that. This is the example of another source, again showing giant outbursts. The origin is we don't know, and some regular outbursts. Okay, so once matter is captured either through stellar wind or from the circumstantial disk, as I said, magnetic field lines basically channel this matter onto the poles of the neutron star. So in the process, it forms an accretion disk. Okay, so and while falling onto the neutron star, so there are different kind of radiation. We get X-rays through Bremsstrahlung, cyclotron, or surface emission, thermal emission from the mound of the thermal mound. So that these photons are seed photons are generated here. Then these seed photons with low energy photons, get inverse Comptonized in the matter in the accretion column, so that we get hard X-ray photons coming out of these objects. Okay, this is how we get low energy and also hard X-ray, broadband X-ray photons from these kind of systems. So at high accretion rate, what happens? Because of high accretion, radiation also is strong. So that's a radiation dominated shock is created at a certain height of this accretion column. So because of that, the photons cannot escape along the column, so they escape through radially, forming fan beam type of geometry or emission. Whereas at low accretion rate, there is no shock, so radiation shock, so photons can escape along the column, forming pencil beam kind of structure. So if you study these kind of systems at different accretion rates, or then you can also see the properties, observable properties from these systems. So this is the overall spectrum. From that explanation, you see different components, black body from thermal mount. This is Bremsstrahlung by the electrons, emission from the electrons. And in some cases, we see cyclotron line features in the spectrum, and also some cases iron lines. So this is the overall spectrum. This is an example. Whereas you see pulse profile. Pulse profile is a distribution of photons around the pulse phase of the pulsar or neutron star. So at different luminosity levels, see, the structure of the pulse profiles are different in different energy bands. So that also gives you some indication about the geometry or geometry of the system at different accretion rates. So basically, this geometry of the accretion and also cyclotronization features, iron lines, all these things. So all these are luminosity dependent. So if you study these sources at different luminosities with broad band facility, then you can get a clear picture of the system. So for that, AstroSat, with its simultaneous capability from soft to hard X-rays coverage, is well suited for this kind of study. So using AstroSat, there are a lot of sources, high mass X-ray pulsars observed during this 10 years. So I am going to summarize a very few results from that. Anyway, this we know. This is basically the lag species, time is 10 microns, that is most important here, and also coverage, energy coverage. So this is the first galactic ultraluminous X-ray source observed and that is with AstroSat also. So it was discovered, this is a new source, completely discovered on October 3, 2017. So pulse period is 9.8 seconds, peak luminosity 10 to the 39, 5 times 10 to the 39, well beyond Eddington level. So as soon as this outburst came, so AstroSat observed this source twice only at this October 17 and 26. Okay. So these are the pulse profile we estimated, basically pulse period of the pulsar, and we found pulsation up to 150 kV with CZTI also. So basically these pulsars are very faint in hard X-rays. However, these sources are so bright in hard X-ray also, we got a pulsation up to 150 keV. That was not seen earlier. Okay. So then, yesterday there was a talk on pulse fraction variation with energy. Here we found that pulse fraction varies from 10% at 2 kV low energy band to 40 to 80% at higher than 70 kV. Okay. So this is basically from pulse timing study. And if you see spectroscopy, so those two observations, low luminosity phase and high luminosity phase. So you see here at higher luminosity, 2 black body components were required to fit the spectrum. Okay. So then, because this temperature is 0.35 and 1.2 keV, we estimated the black body emitting region radius is about 121 to 142 kilometers. And also another broad line was, iron line was observed in the higher luminosity phase. And that is explained in terms of optically thick outflows. Okay. For this source, we had only 2 observations. However, NICER observed this source almost every day for 100, 200 or 250 observations. From that study, again, I am part of that. So we found the gradual evolution of the iron line from low luminosity to high luminosity. Okay. So that also confirms the strong outflow in this source. However, there is no cyclotron resonance feature in this source. So then, this is another ULX, ultra-luminous source again in our galaxy. After that one, first one, the second one. So it was observed in December 2019. So AstroSat monitored this source for 2-3 days. So basically the lines time during this period it was observed. So peak luminosity of the source is 10 to the 39. So because the luminosity is beyond Eddington, so it is termed as ultra-luminous pulsars. Okay. So here also pulsation is 9.3 seconds detected. This is energy resolved, just light curve. It's nothing else. So 0.3 to 2 kV, 2 to 7 kV SXT, and this lax PC. CZT is not shown here. Okay. So pulsations are clearly seen even in the light curve of the source, because I think the intensity or it was at the peak of the outburst, and also pulse period is 9.3 seconds. Okay. So there is a spin up was observed during these observations of 2 days, which is basically the time spin up rate of 1.75 times 10 to the minus 8 seconds per second. So detailed observations of this source in timing and spectroscopy side, it is found that it matches with the earlier ULX, whatever I described earlier. So that is again that is why it is also termed as another ULX in the galaxy. So this is another B XR binary pulsar. So in the light curve, which was showing continuous every orbit one outburst, it was observed at 5 epochs with AstroSat in guaranteed time phase, when the source intensity was very, very low. So the lowest was about 2.5 times 10 to the 35 watts per second, lowest luminosity in 0.5 to 30 keV. This source was observed at 2 different epochs below this luminosity. However, during those observations, no pulsation was seen. However, because of lax PC, capability of lax PC, at this luminosity, we also saw clear pulsation in the source. So if you take these as the limiting luminosity for propeller effect, which is basically, then you estimate the magnetic field of this pulsar as 3 to 15 times 10 to the 12 Gauss in this range. The broad range, because we consider the luminosity in earlier observations when pulsation was not there, and here when pulsation is, that is the range we took and estimated the magnetic field. And here you can see, so hundreds of RXT, these black points are from RXT observations of the same source, and this is variation of photon index with luminosity. It is this basically there's a clear break at a certain luminosity that is called critical luminosity, when the shock formation happens in the accretion column. So beyond or at higher accretion rate, the spectrum is different basically, and below that the spectrum is also different, slope is different. So that way you can see at what luminosity or what critical luminosity this pulsar changes its behavior. That's because of, I think, presence of this radiation shock. And then this is a pulsar which was, I think, discussed earlier in this forum. In the parallel session, there are basically another big X-ray pulsar. I am not telling much about this. So pulsations are detected in up to 100 keV. Again, CJTI coming into picture. So transition from subcritical, like 10 to the 37, that's the critical luminosity of this pulsars, neutron star pulsars. So from subcritical to supercritical level, and that change in luminosity or accretion rate also is reflected in the properties of the pulsar, spectral and timing properties of the pulsar. I am not going to detail. And in this case also, even though it was observed in CJTI range, there is no cyclotron line in the source. Okay, so but there are key POs observed in the source. So at observation 3 and observation 4. So observation 3 means the luminosity was 2.6 10 to the 37, whereas this observation is decreased. So the QPO variation from 60 millihertz to the 42 millihertz because of luminosity. And also they carried out energy dependence variation in the QPO frequency. Also they found that the QPO frequency decreases with energy, which is unique till date. I think it has this kind of behavior is not seen in any of the pulsars. So that is, and that is why this finding cannot be explained by Keplerian frequency model or beat frequency model. We have to do something else to explain this energy dependence frequency of the QPO. And again, based on QPO frequency, they estimate the magnetic field is order of 10 to 13 Gauss. 10 to 13 Gauss means it is falling beyond 100 keV or so if you see cyclotron regions picture in the spectrum. So there are some other sources where QPOs are seen. I'm sorry, I'm rushing through because of time. So these are the sources where QPOs. See, all these sources, QPOs are observed in millihertz range, whereas the earlier talk, the low mass X-ray binaries, where QPOs were at hundreds or kilohertz. That's another difference because of basically disk, inner edge of the disk from the neutron star. In this case, because it's far away, so a QPO feature is related to the accretion disk of the system, and there the disk is extended closer to the neutron star, so the QPO frequency is higher in those cases. So now cyclotron, this is the most important feature in the accretion pulsars, binary pulsars. Cyclotron, I'm not going through this. This is a resonant feature in the spectrum where the photons are scattered away by the electrons embedded in the magnetic field. So in the intense magnetic field of 10 to 12 Gauss or so of the neutron star, these electrons motion is quantized in Landau levels, and the photons with a matching energy, with the difference of the Landau levels, can get scattered away from the line of sight. And that, because of that, it appears as a deep in the deep-like feature in the spectrum. That is what we call as cyclotron region scattering features. And the relation between cyclotron feature and also magnetic field is that. So if you detect this feature in the spectrum, then you can estimate the magnetic field. But the catch here is at what height of the accretion column this feature is happening. So while quoting this is the magnetic field of the neutron star, we assume that that's at the surface. But it's not at the surface because this feature occurs at a certain height of the accretion column. So that means it gives magnetic field at that location where scattering feature is happening. So if you keep observing some source at different luminosity levels, so that will give you some dependence on cyclotron line and hence magnetic field. And the lowest one, I mean the closest one, if the cyclotron, the CRS feature is happening at the closest to the surface, that will give you maximum magnetic field, and that is more appropriate to quote that this is the magnetic field of the neutron star. So again, you need to observe, keep observing the system at different luminosity levels so that you can find, you can say something. So till date, basically these are the only sources where magnetic, the CRS feature is seen in the spectrum. There might be one or two addition because this is an old one. So, but still about 30, 32 sources where the CRS feature is known, even though X-ray astronomy is so old now. Okay. So another interesting point here is this is one source, as I said earlier. This is luminosity, this is cyclotron line energy. You can see here clearly there is variation in the cyclotron line energy with luminosity. Okay, so that means, as I again emphasize, that you have to observe at different luminosity levels to find out or estimate the magnetic field. This is one I am focusing here. This is HX70 data of one pulsar. This is one of this 0535+2262. It went to outpost during AstroSat time, 2020. Okay, so it is this peak luminosity was about 10 crab, so high, extremely high. So HX70 observed at rising phase and falling phase so many times. And this is the track of cyclotron line in the source. Okay. So again, this is critical luminosity range, beyond which you show different feature dependence, and below which it show different features. So unfortunately, with AstroSat, we only had one observation during this outburst. So that gives you 1 point. So so we missed something here. Anyway, so and these are the only sources where cyclone scattering feature has been observed with at a different luminosity. You can see this is beyond critical luminosity is falling, and below critical luminosity is more or less constant or rising. Okay, so that is why you keep observing cyclotron features even though it is known, but at different luminosities, so that you can have some idea of the magnetic field closer to the neutron star surface. So there are several sources with which AstroSat we have observed cyclotron lines. These are the sources listed here. So I am not going to detail. Okay, so I'm sorry for this. So there are three sources where phase result spectroscopy of cyclotron line has been carried out with AstroSat. It is extremely difficult to do it because of lack of photons in that energy range. So you can see the variation of cyclotron line energy with the pulse profile or the flux. It shows about 13% of variation over the line energy. And here it follows the same. Okay. And these are the sources. I might have missed some sources from here, but these are the sources where cyclotron line is seen with AstroSat at certain luminosity. If you put or populate that figure with different luminosity and cyclotron, it gives you some idea about how it varies with the luminosity. And this is the summary. So you can read. So at the end, I thank all the PIs and the team members of all the instruments and the ISRO, of course, because of which AstroSat produced so many interesting results, not only in the neutron star binary, in whole astronomy. So a big thanks to all the members of the team of the instruments here. Thank you.
Thank you, Sachi, for comprehensive coverage despite the shortage of time. Couple of questions.
Sachindra, that I didn't envy you having to summarize all that in just 20 minutes. That was a really good summary. One thing I just want to add, you talked about the source AO535, but I always like to advertise AO538 minus 66. That's in the LMC, and that, of course, I would say if it were being discovered today, it was discovered in 77, we'd call it a ULX. The first ULX, yes. But of course it's in the LMC. And the reason it's interesting, it breaks the period range you gave for the BEX sources. It has a 69 millisecond period, and it's highly relevant now because it's just gone into its second big outburst 45 years after the first one. As you probably know, NISA has found the 69 millisecond again, and they're going to be, I'm sure, following it on the 16.5-day orbit. So that's a really interesting one. I just wondered whether AstroSat has been observing it as well.
AO535.
AO538.
AO538.
Minus 66 was the original name with the Ariel 5 satellite, something back in prehistory.
I don't recall it being observed, but we'll
so, to add to this, one, I think, proposal to the team that because of this HX70 what did very good, fantastic work on cyclotron line variation with luminosity. So even some time or even now, one BX is undergoing outbursts with very high magnitude. So you keep observing for certain day, long periods, so that you can track the evolution of cyclotron line or even other properties, so that it will be like a unique kind of result from AstroSat.
Yeah, thanks. Shantabrata, we'll have to unfortunately close after that.
Nice talk, Sachi. I have a very naive question. As you mentioned that the quasi-periodic oscillations that you see for high mass X-ray binaries and low mass X-ray binaries, they just differ by the accretion column that comes.
No, that's just, I just observation-wise.
No, that's true. So what is your take about the real physical mechanism? I mean,
basically, you can say inhomogeneity or inhomogeneity glob matter in the inner part of the accretion disk. In case of low mass X-ray binary, because the disk is close to the neutron star and is rotating very fast, okay, so it may give you
the high frequency cube.
Sorry?
High frequency cube.
Yeah. So whereas in other case, it is the opposite.
We will have to move on. Thank you very much, Sashi. Next speaker is Stalin. You need to get the microphone. Stalin is from the Indian Institute of Astrophysics, and he is in charge of the UVIT Payload Operations Center at the moment. So if you have any question about UVIT data, this is the person to ask.
No, this front is back. Okay. This is front.
So Stalin is going to tell us about constraints on blazar jets, results from AstroSat.
Okay, so firstly I thank the organizers for this opportunity to present the results on blazars observed by AstroSat. But having heard the talks in the first session, I feel that the blazars as such has performed relatively poorer compared to the other objects studied by AstroSat. In total, there are roughly 23 papers which have come out in the last 10 years, which is relatively low compared to the other statistics, what I see today. So now I'll move on to what are blazars. These are a category of AGN, which are believed to be powered by accretion of matter onto supermassive black holes at the center of galaxies. And when you talk of AGN, a large fraction of these sources do not emit in the radio band, and they are called radio quiet sources. And a small minority, around 10 to 15%, emit large amount of radiation in the radio band, and they are clubbed towards radio loud sources. And what is shown here is the distribution of the ratio of the flux density in the radio at 5 GHz to the optical V band, parameterized by a parameter called R, which is called the radio loudness parameter. And if you plot the distribution of the radio loudness parameter based on the polymer green survey sample, you see a bimodality around R equal to 10. So sources having R less than 10 are called radio quiet, and sources with R more than 10 are called radio loud sources. And recently from the 6-degree quasar survey, again people tend to see a bimodality, and there are concerns among the community that this bimodality can be because of the sensitivity of radio surveys, and possibly in the future this bimodality one may not be able to see this bimodality. And there is a suggestion in the literature that we may tend to call these sources as jetted and non-jetted, and therefore blazars come under the category of jetted AGN. And as you know, these sources emit throughout the electromagnetic spectrum from radio to high energy gamma rays. They come in two flavors, BL-like objects and flat spectrum quasars. And if you see, flat spectrum quasars, they have a strong disk, they are efficient accretase, they reside in photon-rich environment, and they see emission lines in the spectrum. So this is the typical spectrum of a flat spectrum quasar. When you come to BL-X, they are inefficient accretion, a low density environment, and they have featureless spectrum. So this is how the spectrum of a BL-X looks like. Now coming to the broadband spectral energy distribution. So the spectral energy distribution of blazars have a typical 2-hum structure. This is a low energy hum, which is very well understood due to synchrotron processes, and this is the high energy hum, which is highly debated. We do not have a clear picture on the origin of this high energy emission process in blazars. What is shown on the top panel is the spectral energy distribution of a BL-like object, and what is shown on the bottom panel is the SCD of a flat spectrum quasar. So if you see here, the X-ray nicely falls in the falling part of the synchrotron, whereas in the case of flat spectrum quasars, the X-ray lies in the rising part of the inverse Compton hump. And these blazars are also further classified based on the peak of the synchrotron into low synchrotron peaked, intermediate synchrotron peaked, and high synchrotron peaked blazars. And as I told you, the problem lies in understanding the cause of this high energy emission. It is still unsettled, and there are two competing models are leptonic and hadronic. In the leptonic scenario, one tends to see a correlation between the optical photons and the GeV photons, whereas in the hadronic scenario, these two emissions need not be correlated. So now, given this scenario, but people have also found that a single source may behave differently at different times. So what is shown here is the SCD of a source 3C279. And if you see here, the SED is shown for 3 states, low state, flaring 1 state, and flaring 2 state. And you see enormous difference in the high energy portion of the SED. So now how to constrain these models? There are 2 approaches. The first approach is you use variability. The idea is if it is leptonic, they are optical and GV are correlated, and if it is hadronic, optical and GV are not correlated. The second approach is SED modeling. This SED modeling requires simultaneous observation across wavelengths, and this is where AstroSat comes to play a major role. Now coming to the timing part, so here I show the multi-band SED of a flat spectrum quasar, and this is the gamma ray gain, X-ray, UV, optical, infrared, and this is the polarization. So if you see here, there are instances when the GeV and optical photons are correlated, and there are instances when there is an optical flare, but there is no GeV flare. So the conclusion is timing studies will not be able to constrain the leptonic versus hadronic scenario. So what is the other approach? The other approach is to study by a broadband SED, and this is where AstroSat comes into picture, and this is a niche area for AstroSat. So this is demonstrated by a spectral energy distribution of a flat spectrum quasar. So this is the region which will be covered by the ultraviolet imaging telescope, and this region will be covered by the soft X-ray telescope. This is covered by the LUX-PC, and of course, the gamma ray data points are provided by the Fermi telescope. It scans the sky once in 3 hours. So by combining AstroSat observations with Fermi, one will be able to put tight constraints on the cause of the high energy emission process in blazars. So using this thing, there are lots of papers which have come out, but more or less the papers have worked on the same theme of constraining the broadband SED. So what is done recently? We looked into the archives of AstroSat. We selected blazars for which data is publicly available, and we also looked into the constraint of the lag species data having reasonable signal up to 20 keV. So we arrived at a sample of 19 sources, and these are being analyzed in a systematic manner, and you will hear more about this in the talk by Abhijit today, later in the day. Now I'll move on to a few examples. Basically, I have collected all the published papers by AstroSat, and this is one such example. So this is an example of a source OQ334. This source is nearly quiet in gamma ray, except for some time in 2020, we showed a high gamma ray flare. And luckily, this source was also observed by AstroSat within 1 week of the gamma ray flare, and this is the result of the AstroSat observations. So here is the because during the same time, SWIFT also observed, and this is the SWIFT UVOT, this is the UVAT data point, this is the XST data point, and this is the Fermi. Again, modeling the multi-wavelength XCD, the observations from these sources are nicely explained by a one-zone leptonic model. And these are the emission coming from the torus, accretion disk, the synchrotron self-Compton process, and this is the external Compton process. So these results clearly demonstrate the usefulness of the multi-wavelength capability of AstroSat to constrain some of the high energy emission process in blazars. So what is shown here is the variability of the same source as seen in the UV band. Now there is another handle of constraining this high energy emission. Along with AstroSat, here what the authors have done, they have nicely tried to use the X-ray polarization observations coming from IXPE. The idea is based on this theoretical plot. So in the case of leptonic scenario, you tend to see low X-ray polarization, whereas in the case of hadronic scenario, you tend to see high X-ray polarization. So this band represents the IXPE band, this band represents the Fermi band. In the Fermi, there was an initial hint of doing polarization, but they cannot do. For maybe possibly in the future, there's a Compton spectroscope instrument coming up by NASA in the next couple of years, operating from 0.5 to 5 MeV, possibly something can be constrained here. So what these authors have done, they have tried to take a flat spectrum quasar. They tried to observe the source when the source was observed by IXPE, and this is the observations coming close to the duration of IXPE observations, and what was found was in IXPE, the source was not detected in X-ray polarization. It was an upper limit, and when the source was modeled using the simultaneous data from AstroSat, this is the SWIFT data point, this is the point coming from UVAT, this is the SWIFT XRT, and this is the Fermi. Again, this multi-wavelength observations clearly says the SED is well fit by a one-zone leptonic model. This is again on the same idea. People have concentrated on a source called 2344 plus 514. Here also the idea of the authors is basically to constrain the high energy SCD component, and they have considered 4 or 5 epochs where they have data points from AstroSat. Again they model the SCD, and the conclusion is the high energy X-ray component is well described by a electronic scenario. Here these authors have tried to look into the high energy X-ray variability properties of a source. They have focused on two blazars, Mercurian 421 and 1959 plus 650. They have observed the source at various brightness states, and they try to, this is a light curves given from the source, and they study the spectrum of the sources. They found that the frequency of the peak and the shape of the lower and high energy hum varies with the total flux of the source. The same authors again try to observe one more source. Here is the soft X-ray light curves. This is the lag species light curves. What the authors found, they tried to find a correlation between the hardness ratio and the total counts. This is the well-known harder when brighter trend known in blazars. They also tried to correlate the XST and lag species light curves. They found that at some instances there is a correlation between soft X-ray and lag species. At some instances there was a hard lag, and there also they found instances of soft lag. And the authors tried to explain this lag in the electronic scenario. They say that the soft lag may be due to slower radiative cooling, and the hard lag may be due to the acceleration of high energy electrons. And they were also trying to infer the magnetic field in the source, which they found to be of the order of 0.1 Gauss. Here in the same spirit, they tried to again model the spectrum. They did a time-resolved spectrum and time-resolved analysis. They binned the data in units of 10 kiloseconds. Again, the conclusion what they arrived was the high energy particles, they have a simple power law energy distribution. They are injected into the shock front. They move down the emission region, giving rise to synchrotron and inverse content process. And the presence of a fluctuating magnetic field can lead to the observed spectral properties what they see in this source. Again, this is a paper by Akbar et al. In 2025. They observed Mercurian 421, observed by AstroSat in 5 epochs, and they tried to model the data using broken power law, as well as power law with exponential cutoff. And they found that variations in the source, and this variation is driven by variation in the particle index. And they conclude that the variations are primarily associated with the acceleration or escape time scale of the emitting particles. This is yet another paper by 2 authors, Akbar focusing on Mercurian 421 and Tandri focusing on Mercurian 521. Again, they looked into the variability of the source. They looked into the joint fitting of XST and lag species spectrum. This is the broadband SCD. Again, they conclude that the SCD is well explained by a one-zone electronic model. Here, the authors have tried to look into the long-term variability of Mercurian 421. What they observed, they seem to observe some sort of a sinusoidal variation, but they did some systematic analysis, and what they found that these variations are intrinsic to the AGN, and there is no evidence of QPO present in the system. And they also found the variability to increase with energy, and the typical time scale of variability they found is of the order of 11 kiloseconds. This is one of the shortest time scales of variability in X-rays. Again, coming to the modeling, they modeled by a one-zone electronic model, and they found the variability to increase as a function of energy. Again, this is a key result of us. This is one of the important results of AstroSat. What the authors have done, they have tried to look into the XST data of OJ287 observed at 3 epochs. The key result of this instrument, of this data, is that the authors were able to trace the change in the state of the source. So this in 2017, the X-ray was nicely explained in the valley age. In 2018, the X-ray was falling on the rising part of the inverse component hump, and the source again moved back to in the high synchrotron peak source, where the X-ray falls in the falling part of the synchrotron. So this is a finding of the transition of the source between different states. This is an important research published by Dr. K.P. Singh in the year 2022. This is a source. This is the simple conventional things they did. They tried to do the spectral fitting. They tried to do the SCD modeling. And they told they have difficulty in explaining the source in a single one-zone model because they have some TeV radiation data. So they were trying to tell that the SCD is better explained by a 2-zone model. Here again, the authors have studied few sources, studied a source not 229 plus 200. Again, HSP. Again, the conclusion is that the peaks are well described by an electronic model. This is a BLAC. The authors have tried to study the source at different brightness states. So what I will focus is on this brightness state because At this state, we have the AstroSat observations. So they try to correlate the gamma ray and X-ray emission radiation, and they found that both the emissions are correlated to zero lag. The conclusion is that these emissions are coming from the same emission region. They also modeled the broadband SCD, and they told that again the SCD is fit by electronic models. Again, the authors by Diwan focusing on these sources, and Krishna Mohana focusing on PKS 0208-512. These authors also did a broadband SCD modeling, and they also conclude that the models are nicely explaining the one-zone scenario. And this is a comprehensive study recently carried out by Abhijit on 19 sources, and the analysis is being done systematically to investigate any change in the broadband SCD of the source, and I think you'll hear more about this on the talk later in the day today. This is a source done by Ritavan and his colleagues in 2018. This is an interesting piece of work where they plot the light curves in different energy ranges, and when they constructed the PSD, what they noticed was a break in the PSD, which is similar to the PSD break we noticed in high mass X-ray binaries and Cepheid galaxies, and they conclude that there's a possible connection, evidence of an accretion disk jet connection in a high synchrotron peak blazar. This is also an important result coming from AstroSat. The yet another result is on the variability of blazars. You see, blazars are known to show variations across the wavelengths, but one key area where we do not have enough information is on the UV band. Of course, some results were available from the International Ultraviolet Explorer, but that is limited on few sources. A comprehensive analysis on the UV variability of sources were done by Reshma and his group and a group. The sample consists of around 3 dozen blazars. These all are publicly available data done in a systematic manner, and what was found was these sources exhibit variability on hour-like timescales, because these variability analyses were done on orbit-wise bin data. So the analysis is sensitive only to hour-like timescales, orbit-wise timescales. And here is shown the plot of the color magnitude diagram, optical UV color versus brightness, and they noticed a harder and brighter trend. And this harder and brighter trend is seen both in the flat spectrum category and the BLAC category. The conclusion is that the observed UV emission in these sources are dominated by the jet synchrotron process. Okay. Yet another thing, what was investigated was to look into the short time scale variability, because short time scale variability were known in gamma ray of the order of 1 minute. Short time scale variability were also known in optical within a night, but short time scale variability was not known in the UV, but the capability of UV to have fine time resolution observations, we were able to probe the presence of short time scale variability. The idea is simple. We generated 60 seconds light curve on all the 3 dozen blazars, and we found many sources having time scales of variability of the order of minutes. So these are some of the important results coming from AstroSat, and here I will tell you some of the light curves. These are only 60 seconds bin light curves, and many of the sources exhibit significant short time scale variability of the order of minutes. Now, to summarize the key results of blazars, of course, as I told you, the number of publications which have come out of blazars is very small, 23 compared to the papers which has come out in other branches. First is on the UV flux variability of blazars. These are some new results. UV flux variations, spectral variations, the conclusion that the UV is dominated by synchrotron jet emission. Break in the PSD of a blazar in Mercury 421. This is an interesting result. And the transition from high synchrotron peak to low synchrotron peak, and again to high synchrotron peak, is something new which has come out of UV, not UV, AstroSat. And the detection of short time scale variability of the order of minutes. So now, having these results from AstroSat, just a small thought, what to do next in blazar research. So as I began my talk with the origin of the high energy hump in blazar SCD, we do not have a solution. The problem is still open, and people had a faith that IXP may give some clue, but IXP was able to detect polarization only in BLX, and no polarization has been detected in flat spectrum quasars. Probably this lack of sensitivity of instrument, lack of realistic models, possibly multi-messenger observations in the future can throw light on these things. Now, coming to polarization, this is one area which is less explored. Radio polarization, we do have some observations. Optical polarization, some studies do exist, but the observations reveals are highly complex in nature. X-ray polarization, few BLX are detected. FSRQs, there is no detection as of now. UV polarization, there are only 2 detections. One is on NGC 1068, using the faint object camera on the Hubble Space Telescope, operating on 1200 to 6000 angstrom. And there is an instrument called WUPPE, Wisconsin Ultraviolet Photopolarimeter Experiment. This has done some observations on the Sols 3C273, operating from 1500 to 3300 angstroms. Barring these 2 instruments measurements, there are no other polarimetric observations in the UV band. So this is a complex variability in the optical. This is some data taken from the Vainu Observatory in Kavalur. This is from the 1 meter polarimeter mounted on the telescope in Kavalur. As you see here, the correlation between polarization and flux is highly complex. At some point there is a correlation, there is no correlation, so it's highly complex. So what next? A possible approach is one slide I will focus on. It's a possible approach with the potential for a near-term realization possibly in the next couple of years. So this discussion happened at least 5-6 years before when Dr. Srikumar, who was the director of IAA, he was in one of the discussions I remember in his office, he was mooting this idea. Then about a month ago, I met Girish in ISRO for some other activities, and he also told these are some of the possibilities. So motivated by this, I went back to IAA and then tried to explore the possibility. The idea is here, we can go for a simple telescope with the aperture of an existing UV-AT, a simple NUV system, which is easier to realize, because we also lost the NUV in 2018. This needs to be, but the science needs to be explored. The idea is this will keep the momentum of UV going till the proposed insist gets the nod. It's a thought process, just about a month old, and these are some random thoughts. We hear that there are some spare mirrors that are made for UV-AT available with ISRO. So that is, we try to have check with some LEOS people and possibilities there. A single telescope can be made tailored for NUV. In the current system of UV-AT with the NUV and a visible system, which can be used for tracking. In the current NUV system, there are filter wheel having 8 slots. One slot can be used for what? One slot can be used for a polarizer. So in the single system, we will be able to have a polarimetric capability as well as an imaging capability. And when you come to detectors, there are ready-made off-the-shelf CMOS detectors available, and these are some of the companies which can deliver the CMOS detectors, like SRI, Raytheon, and Teledyne. So only thing, we have to have an enhanced UV coating. So these are some of the thoughts which can be put up to have something which can be realized in the near time scale. Thank you. I stop here.
Thank you, Stalin, for a very nice talk. We have time for a couple of questions.
Thanks for a very nice talk. It's a curious as well as naive question. So I was wondering, you mentioned about this leptonic model, which is also XP data has also been fit with the leptonic model. So when we talk about this correlation between your high energy emission and the other lower energy component, how this leptonic model explains the anti-correlation part, which was well explained by hadronic model. So does all the properties can still be explained by leptonic model for all the cases?
So the idea is the low energy is from synchrotron process. Okay, the same electrons which are in the relativistic gels will inverse Compton scatter the seed photons coming from the BLR or the SSE photons. So that will come in the high energy range. So if this process is indeed correct, one expect to see a correlation between the optical and plus the GeV. This is the electronic scenario. In the hadronic scenario, the optical is coming from synchrotron process by the relativistic electrons in the jet. Whereas one thought about the high energy process is because that can be because of proton synchrotron. So if that is the case, one may not see a correlation between the optical and GeV photons. So that is the thought. And now ISP also has observed X-ray polarization only in BLX. So it's very clear the X-ray is because of synchrotron origin in the BLX.
Look.
In 2344 plus 514, I saw very nice big blue bump in your SED. in general, big blue bump is not seen in BLX. So I am little bit suspicious if the data is simultaneous or quasi-simultaneous or data are taken at very different epoch.
You see, when you look up the emission, what we observe, it is basically a sum of disk emission plus jet emission. So there are certain instances when the jet emission dominates, so we may not be able to see the disk component. But at least even in the case of BLX, which is high synchrotron peak blazar, even in the faint state of the source, we seen what? Nice what? Accretion disk component in the multiband SED modeling. Similarly, in the case of flat spectrum quasars also, generally we see what a accretion disk component on top of the what? Synchrotron. So the low energy hum can be nicely modeled by a disk emission plus the synchrotron component. Yes, at low flux state. Yes, at low flux state. Yes.
Yeah. If the hadronic emission is coming from protons, there are two things. One is because you expected intensity will be 2,000 times less. It has implications for the number density.
Yes.
Secondly, why should the polarization features be so different? You made the point that.
So I just taken that plot from the published paper. So they have done some detailed theoretical calculations by Bocher and company. So they have clearly told that in the case of electron synchrotron, the polarization expected in the X-ray and what? X-ray and the gamma ray band will be nearly similar. But whereas in the case of proton hadronic scenario, the polarization they expect is really higher. That's what they tell in the paper. It's a highly theoretical paper, which I just took that thing from the paper.
All right. Okay. Thank you. Let's thank Stalin and we'll move on to the next talk. Request. Srija Karta is our next speaker. She is from the Christ University in Bangalore. She's a well-known expert on galaxies. She's going to tell us about AstroSat UV view of nearby galaxies.
Very good afternoon to one and all present here. And from our university, I thank all the organizing committee for giving us this opportunity to talk at this prestigious 10th anniversary of AstroSat. So from my side, I am Srija from Christ University. So I'm going to talk about the UVIT view of the nearby galaxies. So when you look at the next image here, I have shown the SINGS image which represents the Hubble tuning fork diagram. So when you're looking at the initial, when you compare this with the initial Hubble tuning fork diagram, you can understand that there are n number of new classifications came into this picture, and it is very difficult to separate or understand in detail on what parameters we will separate these galaxies. So one of these basically we can look into so the basic challenge in this bigger system of or universe of galaxy is basically like understanding the star formation across the various environments. So what will be our strategy in order to understand the star formation across the various environments? So for that, one option is basically like UV tracer. So UV is basically a direct tracer of star formation, and it looks, or basically it gives us an idea about the very young star forming regions at long distances, or basically at the galaxy distances, and it maps the basically the birthplaces of the stars. And so regarding this, when so regarding this, the initial time, or basically NASA was, with the Galaxy mission, it was capable of looking at the UV aspect of the galaxy star formation. And then in 2000, Indian astronomy community, they looked for a telescope which can look at the UV universe in a better resolution. So that resulted, basically that resulted in the telescope that we are talking now, that is the UVIT, which is basically a game changer in the area of UV observations. So the main aspect that we already know, like galaxies having an 5 arcsecond resolution, whereas with the UVIT we are able to look up to 1.2, 1.5 arc seconds. So what does this spatial or higher angular resolution means? So when you're looking at a galaxy which is at the distance of 10 megaparsec scale, you can look very closely to the star-forming clouds which are of the size of few parsec, or basically at the 10 megaparsec scale, you can look up to something like 50, 60 parsec star-forming regions. So that gives an additional edge to look into the different aspects of star formation, or basically like the effect of star formation in the galaxy evolution. So when you compare, as we have already done this, like okay, UVIT when compared with the galaxy, you can understand that the star forming clouds, what you look for the same area of the sky, you can see that a considerable difference when you are seeing very clumpy in the galaxy, whereas when you look into the same region in the UVIT, you can see the individual star forming regions very closely. So this is from Ashish's paper. Yeah, so when we got this opportunity of highly resolved telescope which can look into that much of details, many people, or basically many astronomers, were eager to work in this different aspects of this field, and many publications already came in this league of work, or basically research aspect. So the basic research aspects are basically like growth and structure, the star formation dynamics, and the different kinds of environments that these galaxies are belonging to. So some of these works I will be discussing in the further slides. Yeah, so regarding the evolution of galaxies, you can look into the 3 different aspects of galaxy evolution. It can be of secular evolution, it can be of interacting galaxies within the interacting galaxies, or basically it can be the post-major or basically post-interaction galaxies. So when I look into the role of secular evolution in grand spiral galaxies, okay, so the role of secular evolution in the galaxy evolution, sorry. Yeah, so these are 2 examples with which UVIT has observed. One is on the left hand side, as everybody knows, it is the NGC 628 galaxy, which is in another way named as the phantom galaxy, and it is a grand spiral galaxy as well. On the right hand side, it is another galaxy which is also very in the field region. It is the environment is of field. So when we looked into these galaxies, we will be seeing like we will be expecting the secular evolution in these galaxies. So we will look in detail regarding this, what we can learn better regarding these galaxies. So these galaxies are more or less at the distance of all the galaxies which I am going to discuss is almost like within the distance of 20 megaparsec scale. So at this 20 megaparsec, or within that, you can see that okay, you can resolve to the very central star forming clumps or star forming regions. Yeah, so when we looked into the age distribution of these star forming regions, you can see that the inner regions are basically like, you can see an inside out growth, basically like the millennia. So basically it is like, okay, so we also need to understand that with UVIT you can look up to 200 million year of star forming or ages of 200 million year. When instead of H alpha, when you look at, it is only giving an data regarding 10 million year. So in this case, you can see that okay, the massive, or basically the massive aged stars or star forming regions are basically towards the center, whereas the inside towards the extent, it is basically of smaller clouds with basically like very young smaller clouds towards the extent of the galaxy. So that is one aspect you can learn from the UVIT image or UVIT study of galaxies which are near to something like within less than 220 megaparsec. So another aspect with the highly resolved data, what we can do is basically like we are still in a debate like, okay, which is basically providing the spiral arms, or basically what is the reason or how the spiral arms are basically generated, or basically how it is structured in this grand spiral galaxies. So with the UVIT, with this high resolved data, we were able to look into that aspect. So we understood that, okay, basically we have divided the two spiral arms, and we looked into the age gradient in each of the arms. So when you looked into the age gradient of these galaxies, this particular galaxy, you were able to understand there is no age gradient that you can see in either of the spiral arms of this galaxy. So if you were able to observe a gradient which is there in the age, that means like, okay, there is a spiral density wave which creates the spiral arms in these galaxies, but we are not getting a clear idea regarding that. So maybe like swing amplification, another reason for the spiral arm creation, can be a cause for this particular galaxy which is observed using the UVIT. So during this work, it is basically like, okay, JWST, the first images came from the JWST. So the JWST, what is the good thing with combining the JWST with UVIT? So UVIT means the young star forming regions, whereas the UVIT will give you the dust, or basically how these star forming regions affects the fuel over there. So we combined basically the JWST with the UVIT data for this phantom galaxy and another two galaxies which was available from the JWST data. So we studied the PAH molecules, or basically the correlation of PAH molecules with the UVIT, or basically the FUV and UV. So how we did that? So we checked the star forming regions regarding the different bands in the different bands of the pH molecules. So the three different bands which we used in this case is like 3.3, 7.7 and 11.3 micrometer bands, which is from the JWST that we combined with the star forming regions that we obtained from the UVIT data. So when we combined and we took the ratio between these pH bands. So this is the data basically. So we should appreciate the UVIT regarding the wider field of view that is given in the top images, whereas the red boxes are basically the data from the JWST. So even within that, we were able to come to certain conclusions. So that are basically like, so this is a plot where you are seeing the ratio of different bands of pH. So that you have to read it in a different way, like, okay, from the table you can understand that if 3.3 is higher, so that means that is contributed from the smaller neutral molecules, whereas 7.7 comes from the larger ionized molecule, or basically the 11.3 comes from the, or basically it represents the large neutral molecules from the in that star forming regions. So in all the three diagrams, or the images, the band ratios, you can see that as the star formation rate increases along the x-axis, you can see that the ratio also increases. So the last plot where you have 7.7 with respect to 11.3, I will explain. So that is basically like both are coming from the large pH molecules, whereas one is ionized, whereas one is neutral. So that implies that it is mostly depending on the ionized one. So what we finally concluded from this work is basically like the star forming regions are mostly from the ionized smaller pH molecules. It's mostly the presence of ionized and smaller molecules. So what might be the reason for this? So basically it is like the high energy, or basically the high temperature at the star forming regions might be breaking up the larger molecules into smaller ones, and that's why we may not be seeing the larger molecules, whereas we are seeing the larger fraction of smaller ionized molecules in this star forming regions. So we also try to see that whether any correlation between the larger sigma SFR, where is sigma SFR and low sigma SFR surface density. So what we finally come up with is like it is different from the population associated with star forming regions, which is relatively lower and higher SFR surface density. So the fraction of the ionized molecules might be a reason for this particular difference between the high and the low star formation regions. So in the individual galaxies, we have also looked into the resolved Kenniget-Schmidt law. So we have already seen that, okay, what is basically the, regarding the star formation, what is basically the Kenniget-Schmidt law. It basically tells that for all the galaxies, it might be a linear relationship. So when we looked into these three galaxies, which has bar as well as the AGN in the center, so we finally come up to a point that it is not a one-on-one relation for all the galaxies, but in this particular set of three galaxies, you can see that for 1566, it is giving a one-to-one correlation that says that whatever the molecular cloud, molecular gas which is available to the system is completely converting to the star formation, whereas it is not the same for the other two galaxies. So we have looked into the different aspect of it, and finally we come to a point that rather than the central bar of the galaxy bar in all these galaxies playing a role, it is more like the dependence of molecular gas, which has a major role in converting the gas into the or creating the star formation efficiency. So the star formation efficiency also gives a lower or a negative correlation with the molecular gas in this all the three galaxies. So probing to the effect of interaction. So this is one of a galaxy we have studied regarding the interacting galaxies. So this is one galaxy, the major one galaxy is 1512, and the satellite galaxy for the same is 1510, where you can see that what might be the role of, or who is creating, or the role of interactions in this galaxy. So we might be expecting that since it is an interacting galaxy, it's only the environment, or basically the satellite galaxy is having a huge role in this one. But when we studied this, we also found that it also has a secular evolution. So how to confirm that? So this galaxy is having a bar in the IR, whereas it doesn't show the bar, galactic bar in the optical or in the UV regime. So that also we have to identify. So how to confirm that it has the secular evolution? So in the nuclear, so the central nuclear ring, okay. So this image shows like, okay, when we looked into the contribution of secular and environmental factors, we found that near to the 1510, that is the smaller galaxy over there, so you can see like it has, due to the interaction also, it has a star forming enhancement in the galaxy, and also it has secular evolution as well. How to confirm the secular evolution? It is from the nuclear ring. So the nuclear ring in the bar region, it's basically like at 45 to 225 degree angle from the north. So when you looked into the contribution in the inner ring of the galaxy, you can see that the heightened star formation you can see at 45 and 225. That implies like basically the gas in the galactic bar is basically funneling towards the ring, and it is enhancing the star formation in the ring region rather than in the central galactic bar. So it basically tells that in the bar region, it is basically the quenching of the star formation is basically happening, whereas in the ring, it is enhancing the star formation. So that implies like, okay, the central secular evolution, whereas the environmental effects that happens to the outside of the galaxy. So along this direction, we have studied other three galaxies. So these are the three galaxies which are in the interaction, and where you can see that when we looked at the different correlations for this star formation enhancement, when it comes to the interacting galaxies, we found that the pair mass ratio is having a role in this enhancement of the star formation. So we have also looked into the interacting galaxies which are towards the cluster region. So this is one of the galaxy which is in the Virgo cluster. You can see that towards this direction it is basically moving towards the Virgo cluster center is towards that direction. So that direction has a higher star formation surface density as well as the molecular gas is also higher towards that. So what does that imply? So when you are having a higher molecular mass, that is basically converting to the star formation, and it is having a effect of the ICM, which is through which it is moving to the cluster center. So this star formation enhancement, whether it has any global relation, when we looked into the ram pressure galaxies of the Virgo cluster, we found that in this one, the blue points are basically like the ram pressure stripped galaxies, whereas the red points are basically non-ram pressure stripped galaxies. And at the R200 radius, you can see that this is towards the center, and R200, at the point of R200, the star formation rate is getting enhanced for the ram pressure stripped galaxies, whereas for the non-ram pressure stripped galaxy, it is basically declining. So till that point, it is basically having a 1 to or more or less similar kind of star formation for the non or ram pressure stripped galaxies, whereas towards the inner region, it is having a different trend. So what might be the reason for this? Basically the internal characteristics, or basically the object is resistant to the ICM through which it is traveling. So that we have to look into in detail for this particular galaxies. So post-interaction phase, I will just conclude with one title. This is basically like post-interaction phase. There are certain peculiar galaxies which are into this group. Basically one of that is PRG, or polar ring galaxy. Polar ring galaxy is basically having a galaxy in the host galaxy in the center, whereas it has a ring of gas and dust in the polar axis. So that is basically like with the given examples here up. So I will just conclude. So we just having these 3 galaxies which are in the league of PRGs, and we looked into in detail regarding the evolution of these galaxies. So we found that so these galaxies in the color mass relation, it is very difficult to place these galaxies. When you combined the UVIT with the molecular mass, or basically ALMA or Mirke data, we were able to place them properly in the color mass relation or color mass plot. So where you can see that 3718 is in the star forming region, that is very actively, or basically just after the interaction it is, whereas the 2685 is getting into the green valley, whereas 4262 is coming out of that towards the red sequence. So the summary of the talk, and before that I would like to thank, or basically thank all the organizers for giving the opportunity to talk in this particular decadal meeting, and thanks to ISRO for the announcement of opportunity AO funding, and also thankful to all the PhD scholars, postdocs, and the MSc students with whom we worked with, or basically worked with us, our group, and also thanking to all the collaborators which are part of this work. Thank you.
Thank you very much. Thanks for this nice summary of the insight we are gathering about nearby galaxies with UVIT. So a couple of questions. Kanak.
Hi, Srija, nice talk. I just had a question on the spiral arms when you identify clumps and you measure their ages, right? Do you have some confidence on the age measurements?
So there is as you, I can understand what is the question. So what are the models with which you are basically calculating the age there, right? So it's basically like the confidence is that, so that's why we kept the age the bins in a statistical way that, where you can have a more or less trust. So that's why we have kept only that bins. It's not like, few tens of millionaire we haven't done. So it's more or less like ages greater than 100 and something less than 50, and whatever comes in between we kept in, so that we are seeing like, okay, an inside out growth. So there are other papers also in the similar manner, they have estimated the age, like, okay, the age of the star forming clouds.
I see. I mean, I just thought, because you know there are uncertainties which is depends on the, whether you, depends on the star formation history, constant star formation versus bursty, then the metallicity, the big energy.
So,
that's what,
Any other question? Yes.
My question actually is already asked, but my questions were related. So first, how did you calculate the ages, and what was the improvement in the uncertainties when you're calculating the ages from the UVIT and doing it from the GALAX?
GALAX, basically you can see that, okay, the GALAX age estimation is very difficult because, as I already told, in that particular galaxy itself, you were able to see the star forming clumps of something like 50 parsec range, whereas if you are looking through GALAX, it is something like 200 or further beyond that. So that much smaller clouds itself you were able to distinguish. And also one more factor, there is obvious errors in that, but within the error limit, we are saying that, okay, there is an inside outgrowth. So one more aspect which I want to connect with that is, it's like for the same galaxy we have looked into the JWST. So JWST has a much higher resolution. So when you connected it with the JWST data also, these clumps were aligning with whatever the results coming from the JWST.
Thank you very much. Let's thank Srija once more.
Thank you.
Next speaker is Varun Bhalera from IIT Bombay. He is leading the astronomy group there. And he has been a member of the cadmium zinc telluride imager team from the beginning, since before launch, and is an expert on transient observations of all kinds. He's going to tell us about a decade of GRBs with CZTI.
Thank you, Dipankar. So it seems to be standard practice that I stand between people and food. You were expecting to get lunch, and here I am giving food for thought instead. I'll start with two acknowledgements and auto-advancing slides apparently. But first is thank you to ISRO and AstroSat, the entire team that's been working on this for almost 3 decades at this point, without which any of this work would not have been possible. And second, I want to start with a confession that although here I am talking about GRBs with AstroSat today, a decade ago when Dipankar and Rao and Santosh told me to lead this effort, I did not believe we were going to find any GRBs. Okay. Fast forward, let's just have a quick overview of what GRBs are. Option 1, you have a massive star, core collapses, and you have a black hole, accretion, jets, or you have 2 neutron stars over here which merge together, collide, and again launch a jet. The common theme is blow things up, you get cool results, and if you happen to be along the way, then A, if you are close, you die, B, if you are far away, you publish papers, right? So if the relativistic material that is getting out of this, with moving with gammas of hundreds to thousands, if it points at you, you see this extremely bright flash. Now, when AstroSat was, okay, jokes apart, why bother studying this? These are the most intense environments that we have managed to get in the universe since the Big Bang. So if you are wanting to study high accretion rates, relativistic physics, effects of magnetic fields, radiation mechanisms, these are the most extreme labs available in the universe at scales which we cannot and should not replicate on Earth. All right, so actually the history of GRB studies goes back a long time before AstroSat. The first paper I could find about GRBs in India is 1977, and you can see Kasturirangan, U.R. Rao, Marar and Iyengar as co-authors in this ICRC proceedings from 77. Later followed by SROS-C, which was going to detect GRBs, and then of course they did here. I think Sita is also co-authors on these papers. So, and I'm sure there are others in the audience as well. So GRBs, the study did not start with AstroSat. We did take it a lot further with AstroSat. Okay, so when this came in, the original idea was that there's a hidden feature in CZTI known as the side coding. So if you take apart CZTI, then in about these parts, okay, this is the radiator plate which is conspicuously missing from the model outside because that doesn't need to radiate as much heat. But on that side we have these two coded mask patterns, and the idea was that if a GRB were to shine from this side over here, we should be able to localize them using this. Spoiler alert, didn't work. Okay, but on the very first day that AstroSat started operations, so we launched in September, we waited for 2 weeks for outgassing, and then CZTI was switched on, the first instrument to be switched on, and on the very first day we saw a GRB. Okay, so the first scientific result from AstroSat that was published was actually the discovery of GRB 151006A. And now we have 782 GRBs and counting. And when I say counting, I'm serious. I had to change this slide today morning because 2 hours ago we published GRB number 783. So that work is going on. And we have seen GRBs all over the sky. Even in satellite coordinates, we have seen them all over. And most of these GRBs have been detected by CZTI, not all. I'll come to that in the end. So how does it work? We start with observational data. We do slightly specialized processing. For example, the usual pipeline sees spikes in data as noise, and it removes those, whereas that's exactly what we are looking for. So some things are changed. Then we do GRB searches through a lot of different methods. So there is a machine learning based pipeline that is operated. There is a full package called SIFT that we have been working on. There is a sum threshold algorithm. The processing is done at IIT Bombay and at the Payload Operations Center in Ayuka. What we call triggered searches are inputs coming from somewhere else, some other GCN or ATEL which says there was a burst. We go and look at AstroSat data to see if something was found. And after we find these GRBs, we start measuring their properties, which means that we will either publish them again as GCNs or we communicate them to IPN. We put them all on the GRB page and the URL is right there at the bottom. Or what we will also do is, if the GRB is interesting enough, we will go for more detailed studies. And there are a lot of talks and posters about this in PS3 and the ST7 sessions. Okay? So we found them, and we found a lot of them. We found GRBs which last for a fraction of a second. I know the bottom axis is probably not visible, but these pulses are less than a second here, whereas these pulses, which look similar, are on a zoomed out time scale lasting about 50 to 100 seconds. Okay, but just finding them is not enough. For the first year or two, we just published counts and T90 measures and so on. But then we started working into localization and spectroscopy and polarization of these bursts. So how did we do that? Well, let me give you a couple of examples. Okay, in 2017, gravitational wave detectors in January 2017 identified a black hole merger. And then 2 days later, in that, now LIGO gives a rather large part of the sky as an uncertainty area, and a fast fading optical source was detected. So people got quite excited because that fast fading optical source did look like a GRB afterglow, but the usual suspects had not seen a GRB. So the question is, okay, can black holes suddenly start emitting light when they merge? So here's what the optical data looked like. And if you fit a power law, which doesn't look like a straight line because this is a linear plot on this axis, it works like this, but if you zoom in and look closely, that black line is not following data, right? The data seem to go more like this. And if you fit that power law, what you actually get is a different time. Okay, that line is missing from this plot from some reason, but you get a time here, and exactly at that point we found a GRB with AstroSat. So there are 2 papers on this source. One which says, oh, we think black holes might actually emit light, and one which says, no, sorry, this is actually a GRB, we found it. Here's an example of science by non-detection. GW170817, the famous binary neutron star merger, which was studied, the only source still studied in both gravitational waves and in electromagnetic radiation. Fermi GBM found a burst which it said was located somewhere here in the sky. And based on their data, we calculated that it was bright enough that AstroSat should have seen it. We saw nothing. Okay, and the reason we saw nothing eventually emerged that this part of the sky was Earth occulted as seen by AstroSat. Okay, and we were so sure of it that when we were directing the growth collaboration about where to search, we said don't bother searching in this part, it must be here, and eventually the source was found within this part right here. Okay, so this is the location of the final source. So the localization, even by saying that it wasn't in the part of the sky that was visible to us, was already an interesting result. It improved a lot more when we built the mass model for AstroSat. So by building the mass model, what we started doing, so this is Sujay, who's somewhere here, and Tanmay, who's not around, a lot of people working on it. This is essentially a Giant-4 simulation where we can irradiate the satellite with simulated photons coming in from one side. It calculates all the interactions, saying what fraction will be absorbed, what will be scattered, and what that allows us to do is create plots of what we expect a GRB to look like on our detector plane. So what you see here is observed data, and over here you see simulated data, and they look reasonably like each other. So we can actually use this not just to analyze GRBs, but to localize GRBs. There is, by the way, going to be a poster by Ashish about this. So if you go look at posters, you can look more into this and how it can be applied for Daksha. We also use IPN to localize GRBs. So here the idea is simple. You have two spacecraft A and B. GRB happens there in that corner. The light coming reaches spacecraft A before B, and the time difference between the two signals that you receive is going to help you figure out what this angle was. Okay, if you have a GRB along this line, you get the maximum time delay. If it is happening up there, you get the minimum delay. So for the last year or two, we've been working as a part of this interplanetary network, which uses multiple spacecraft together to actually localize GRBs. So here you see a bunch of annuli, and the blue lines here that you see are actually coming from Conus wind and AstroSat time difference from each other. And we have combined the data with integral, with Fermi, also marked again our Earth occultation regions by various sources. The GRB that we published today morning, that data right now is being sent to IPN because again that was not well localized by anyone else. And these actually helps us narrow down our GRB locations quite well, which then helps us to follow up in other wavelengths. Coming back to the mass model, how does the localization work? So what we did was we divided the sky into a uniform pixel grid called the HTM grid, and then we simulated the response, and these are pre-computed things that we've done in the IUCA cluster and saved there, where suppose a GRB were to happen here, we would get an image that looks like this. If a GRB happened here, instead the image looks like this. So you can see there's a hotspot here, whereas a hotspot at this point is missing. So each part looks slightly different. Now this of course is simply a qualitative comparison at first, but we don't do science qualitatively, right? We have to do it quantitatively. So here what we have is an actual GRB, actual data that was measured for one such burst, and we then can start computing the chi-square comparing this data with this data, and the DPH here stands for the detector plane histogram, and after calculating all of that, you can basically create localization maps like these. So we now have maps like this which are being generated. We've calibrated the uncertainties based on a sample of about 30 GRBs, and the project is now underway to extend this to about 100 out of the 800 or so that we have detected so far. The consistency check here, by the way, you can see that the lowest contour is here, and the X marks the actual location of the GRB as known by Swift BAT. Okay, so we've done pretty well with this localization as well. We also managed to use the mass model to do spectroscopy. And now this actually is a technical feat that deserves attention. So what we are doing here is we have modeled the entire satellite, okay, and radiation is passing through other telescopes. It's passing through internal components of the satellite, and it is getting absorbed and scattered and re-radiated in different fractions. And we are seeing the fully processed result of it on our detectors. And based on this, we have to recreate what the source spectrum was. But this has been done successfully, and a place where it really helps is that if there's a burst that is detected only by Swift, but not by Fermi, the typical GRB spectra are fitted by something called a band function. So you see a power law and a turnover that happens at hundreds of keV and then a steeper power law beyond that. Now the sensitivity of Swift-BAT, which has been a very important satellite in detecting and characterizing GRBs, ends at about 150 keV. So it cannot typically measure that peak energy reliably, and it cannot measure the later decay. But with CZTI, you can see that the moment we added in this is just one example from Tanmay's paper, we can actually start measuring these indices. The uncertainty and the systematics on this are rather large, but the fact that we can do this at all, given that we are extending the range of energies far beyond the design considerations, and we are using this for science which was not at all envisioned when the instrument was being launched, is fantastic achievement. From there is probably the most exciting set of results that we have from CZTI are actually to do with GRB jets and their polarization. Okay, so what happens is that the way this jet is launched is that there are magnetic fields that are present in the jet, and we do not fully understand their role. And if you look at just the spectrum, there's a whole set of models that I'm not going to go into detail about, and I'll give the reason for that in 2 minutes. But there's a whole set of models that can potentially explain the observations. How is, whether Compton is important or synchrotron is important, whether the magnetic field is ordered, radial, toroidal, or completely random, we don't know this. But all of them will produce different polarization signatures, and we can actually measure that. So if you have photons that are incident on a pixel, they can sometimes Compton scatter if they are higher energies, few hundred keV, and they will Compton scatter in any random direction if it is unpolarized light. Instead of that, if you have a polarized light with, let's say, polarization in the plane of the screen, then the the preferred scattering direction is perpendicular to that. If I change the direction of polarization, then the direction of scattering now changes. And by measuring these, if you look at all of these 2 pixel events, so I take a central pixel and its 8 nearest neighbor, you get a 8 pixel histogram, which actually shows a near sinusoidal modulation, and we can use that to measure polarization of gamma ray bursts. There have been a few dedicated missions that have tried to do this. The most notable one was a Chinese mission called Polar, and we've actually got better results than Polar. Currently, AstroSat is the instrument with the largest number of GRB polarization measurements. There are a lot of talks that you should go to for this in the parallel sessions. And what is also interesting is that we actually then went and teamed up with the Polar team, and we are now undertaking a massive joint reanalysis. We rewrote our entire pipeline to work with their pipeline, so that we will compile for everyone a total catalog of GRB polarization. So you should look at these talks to get into a lot more details on this front. The same techniques that were developed to search for GRBs, we could use for a lot of other transients as well. So what is seen here, for example, is a lot of attempts to measure emission from black hole mergers. And the reason for doing this is that the first binary black hole merger, 150914, Fermi claimed a detection which gave it an absolute luminosity of about this line. Okay, and what we did was that based on all the data in O3, we analyzed all of CZTI data to see if there was any emission. Lot of fancy calculations in this paper, but we could conclusively rule out at some 97% or so level that those sources cannot be as bright as what Fermi claimed. Fermi itself, to be fair, said that there is a good chance that this might just be a chance coincidence. It was a low sigma event. Similarly, we have published a catalog of upper limits on X-ray bursts, and we have both the largest sample, X-ray emission from fast radio bursts, FRBs. We don't fully understand what fast radio bursts are. There are a lot of models. Some of them predict X-ray emission, some don't. This is the largest sample and the most sensitive upper limits that have ever been compiled for hard X-ray emission from FRBs. So these searches we were able to carry into other science areas as well. Okay, not just that, after the lessons that we learned, so as I said, in 2015, I was reluctantly looking at GRB searches. I wrote a code which then me and my students and POC team improved upon, and we created a Frankenstein's monster. Last year we said, okay, enough of this. We have rewritten the entire framework to be completely generic so that it can actually be run on any time tag data. Now, GRB searches have not been done only by CZTI. LaxPC has published about 7 GRBs. There is a new result that I am hearing about from SSM. They have detected at least 2 GRBs. But this pipeline can now be run on any mission where we have time-tagged event data. And in fact, IIT Bombay students use the same algorithms and tools to study XSM data to actually find solar flares in that. So this is work published based on the same backend that we have developed. But now we have changed the backend to make it much easier to do any of these sources. So in the last minute, I want to point out that this has not been complete. There has been a running joke internally that how do you know a GRB is important? And the answer is that it's important if we miss it. So if you look at the most famous GRBs of last decade, we missed most of them. At the bottom, the one that you can't read is a GRB that is usually just called the BOAT, brightest of all time. It was Earth occulted. EO means Earth occulted, SAA means AstroSat was in the South Atlantic anomaly. Now this 50% missing fraction is guaranteed for any satellite that's in low Earth orbit. Okay, which means that going forward, if we want to fix this, we have to go beyond one satellite. That is exactly what we have proposed to do with Daksha, where we want to build a pair of 2 satellites. This will have a volumetric coverage that is 13 times higher than SwiftBat, 5 times higher than Fermi GBM. If you want to know more about Daksha, then just go to dakshasat.in or you can scan that QR code. And this is a mission which is under consideration right now. And if it is approved, then we will take all the lessons that we have learned from GRB studies in AstroSat and go much further, be able to do much better. It is not just about GRBs, so I will leave with this slide finally, which is all the other science that can be studied with Daksha. And as promised, I have finished before the timer turned red. Thank you.
Thank you, Varun, for this excellent summary. We can have some questions. Shanta.
Nice talk, Varun. I just want to know that this, you mentioned about 700 plus GRBs. Its energy budgets are already listed somewhere so that this can be used for some other analysis?
Most GRBs don't have a known redshift. So maybe barely about 10% of all GRBs discovered in the world. Someone can correct that number if they have a better idea, but order of 10% are all where we find an optical counterpart at all. And then a smaller fraction of those, 10% is maybe the number for which redshifts are known. Now, we have been able to localize only a small fraction with AstroSat. So if you want to talk about absolute source frame energy, that's not known. Another factor is that you measure what is called the isotropic equivalent energy. From that, if you want to go to the actual energy, you need to know the jet opening angle, which is even harder to measure. And that has been measured maybe for a couple of % of GRB.
Yeah, exactly. I mean, this theoretical modeling remains always challenging unless this information is not ready to happen.
So we are working towards, not through this, but through Growth India Telescope and other projects, we are working towards assembling a larger catalog of this. Not just that, we've had discussions with people from the COSI and Starburst and other teams. If you look at the next generation of GRB missions that is coming up, the fidelity of data is going to be far higher. With Daksha, for example, you will have enough SNR to uniformly divide a GRB, a bright GRB, into 10 millisecond bins. And then you do not currently have theoretical models. You could do analysis of, say, X-ray bursts we heard about in previous talks. You know what a photospheric radius expansion burst looks like. You know what to do with that data. If I give you high SNR 10 millisecond spectra of GRBs right now, nobody knows what to do with it. So we are actually working towards putting out a white paper that is kind of a call for theorists to come up with models and also implementable models that observers can use, right? Some kind of a package like Afterglow Pi or something like that, where I can actually put in GRB data and try to fit it with physical spectra rather than just band functions.
Vidushi and then Sita. Go ahead.
Okay. So interesting.
Aru?
Yeah. So regarding FRBs, so you mentioned about this upper limit detection on the X-ray band. So did it help in like probing the origin of FRBs? It's very, and magnetars is plausible one of those origin of the FRB. So did it, can it help us in getting some insights about the origin of FRBs?
The answer is yes, but barely. There are so many unknowns for FRBs that I find it quite comic. There is a paper that is called FRB CAT. Okay, there is a catalog not of FRBs but of FRB theories. And there are order of 100 theories. Now the most extreme of those can be ruled out, but those were not something that people believed in anyway. So in FRBs, in other bands other than radio, we are in that very early field of early stage of a typical astrophysical field where we are very slowly and methodically pushing down on the bounds. We have also done targeted studies under a program called DWF, Deeper, Wider, Faster, where order of 40 telescopes on ground and space together point to the same set of FRBs. Even there we didn't find anything, and another paper in that is in prep. So we've been pushing down. There has been an X-ray detection only of one FRB so far, which is the galactic magnetar, and the sensitivity in X-rays for extragalactic is few orders of magnitude less than that. So we have not been able to rule out any mainstream theory yet.
I see. Thank you.
Sita?
Yeah, using your giant modeling for localization, first, how long does it take to do that, complete that modeling for the hemisphere you can see? And then what is the accuracy which you get? And how do you propose to improve it with Daksha? How much will you get?
Okay. So first is that we are not, so running the full GANT4 calculations took a couple of months on the Ayuka cluster. But once that has been done, that is no longer a bottleneck. So now, once the data reaches the POC, we can have localization. So it takes about 2 minutes for the data to go from POC to IIT Bombay and then localization in 10 minutes. So the typical latency for getting data for from AstroSat, by the way, has been 146 minutes. Okay, that's a very large number. So after a burst happens, after a random burst, it is typically 146 minutes before data reaches the POC, but in 10 minutes after that we can have it localized. That's answer one. Answer two is that because this was not designed to localize things, the localization naturally is quite poor. We get areas of hundreds of square degrees, and we can localize only the brightest bursts right now. As I said, there's a project underway that is trying to improve this in another 6 months or so. So there's a master student at Ayuka who's working on the, at IIT Bombay who's working on this, and in another 6 months or so we'll have another paper, but it is not going to go down to even tens of square degrees. It will still remain in the hundreds, but we can go from ultra bright GRBs to moderately bright GRBs. With Daksha, the faintest GRBs that someone like say GBM can detect right now have fluences of few times 10 raised to minus 7. Okay. A GRB with a fluence of 10 raised to minus 6, we can localize to 1 square degree with Daksha, right? So that is what Fermi would call a faintish GRB at this point. GRBs of fluence of, let's say, 10 raised to minus 7, which Fermi won't even be able to detect right now, those we can localize to about 10 degrees radius. Now that seems large, but there are a large number of ground-based projects like GoTo and ZTF and LSST, and just today I heard about a new Chinese project called GOTA, and all of these can actually tile hundreds of square degrees of the sky very easily. The focus for Daksha is anytime you want to increase your angular resolution, you are necessarily trading off for either field of view or sensitivity. The global community has very nicely figured out how to study a transient if we find it. Right? And that is where the success story of PTF came in. That PTF was the first major mission that separated the job of finding and then outsourced classification to P60 and P200. So we want to repeat this. Nobody has done that for space right now. So we want to repeat that with space, saying we want to have every single square centimeter of the satellite dedicated to detecting transients. And once we detect something out there, then the follow-up game is a well-settled question.
Thanks. A question at the back?
Barun, for GRB localization, these templates that you showed, a couple of templates, which you mentioned, then you compare against the observations, those templates seem to have some bright spots, single bright spots. Why is that?
So there are two reasons why there are single bright spots. The first reason is that we are actually, the physical size of those spots is They are not single pixels on the detector. In the plotting, these were 4 by 4 pixel groups binned together. And you actually have features, so that is about a centimeter scale. And you have centimeter scale real features in CZTI. So that's reason number one. Reason number two is that the mass model is incomplete. There are parts that we had to approximate because the internal details of the satellite bus are not fully available, for example, which you know very well about. And then there are some parts where we had to make approximations because too fine structures will kill Giant in runtime and so on. So in a few specific directions of the sky, we get artifacts from incompleteness of the mass model, but those are well understood and we can quickly identify them and remove them from the localization part.
Rama.
I can repeat your question.
FRBs,
No.
which you showed, that statistics is from which instrument? Is it?
Okay, this is
And
refusing
has,
to, can you click on this so that I can go back again, please? Okay, so what we have here in these three colors are searches from CZTI. So that is the statistics that we have assembled, and then these down here, if I remember correctly, one is from BAT and one is from integral. So we are comparing the samples with them, and what is plotted there is the X-ray to radio fluence ratio.
And has these been in the catalog of FRB earlier observed by other
So what we did was we took the FRB observation catalog, which includes CHIME and everyone else. And then for all of those we cross-matched with CZTI. Wherever the source was observable and not earth occulted, we were not in SA. So that gives roughly a 50% coverage. And then for all of those together, we have these upper limits.
Okay.
What has also improved, I forgot to mention this, is that between our earlier searches, the pipeline that we used to call SIFT version 1, version 2 gives us almost a factor of 3 better sensitivity because we have better understood our noise characteristics.
Okay.
So it took a lot of, so while the pipeline is generic enough, understanding the noise properties of CZTI background took a lot of effort, and that is what has allowed us, a factor of 3 is huge, right? We got a factor of 3 improvement in our searches this year as compared to 5 years ago.
And there is one repeater which is observed with the multi-campaign mission, and AstroSat has observed that same 2018, 09 something.
So we've
There
observed multiple repeaters, we never got anything in
Yeah,
it.
actually that has in SXT and LAX-PC a signature, which is now being compared with optical and radio observation. GMRT was also coordinated for that. But CZTI, when I looked at, I didn't find any signature, so I can take your help.
So we've looked at LAX-PC data for that, and we think that it is a chance coincidence. We don't think it's
But
real.
SXT clearly shows a signature.
SXT I have not looked at. We can talk about it offline.
All right. Yes, Vidushree.
Also question. So one thing is like you told like there are a lot of GRBs which are missed out. So what do you think, how many number of GRBs will increase as compared to CZTI with Daksha?
Oh, that number is going to be huge. CZTI does about 80 GRBs per year. We are the 3rd largest GRB mission in the world right now, which again is amazing because we weren't designed for GRBs. Daksha, so global tally right now is something like 300 to 350 GRBs per year, all missions put together. Daksha alone will do 550 GRBs per year.
Okay, and the second is for low luminosity GRBs, which are new class of burst and fast transients. Do you have comment on that science cases? Like, would that be possible with Daksha?
So, low luminosity GRBs, the obvious comment is yes, we will be able to detect them. The second part of the answer is no, we don't know what they are, so I can't comment in more detail, but we are talking about taking up a project on understanding that. So taking, for example, EPFXT transients and seeing what likely detection rates we would have in Daksha low energy instrument and medium energy instrument as well, and seeing what science could potentially be pulled out of that is a project we want to take up.
Okay, thanks.
Okay, very last question.
So just note that I was done. You all are now keeping yourself from lunch.
Okay, just you said that only the 7 GRBs the LAX-PC has been detected.
So it is just to make you update that 7 GRBs are that unique GRB detected by the LAXPC, apart from the CZTI, where the couple of the CZTI has been missed out. So only those are being mentioned in that.
Correct. So I said 7 were published, not detected. I'm very sure there are a lot more.
So that's why the LAXPC has detected all the GRBs what CZTI has detected.
Fantastic. Okay. So we should actually have that also put out as a complete catalog. LAXPC has much higher sensitivity for GRBs than CZTI. So the complete catalog from LAXPC will undoubtedly be larger. That said, LAXPC background has more systematics than CZT background, and it will need a lot of work. As I said, it took us 5 years to get that factor of 3 sensitivity. So it is something that can be taken up and I think should be taken up, but has not been done in a systematic scale that way just yet.
No, Tilak, I think that is a very important part. These two must be combined. Okay, so, no. But I think we will...
That was a basic idea. Yeah. We meant only the published which the CZTI missed, and LAXPC had different distinguished GRBs features. We have published on those. And so we expected that the user who are looking the CZTI data should cross-check the LAXPC also once. So that we have going to put once in the POC. So.
Thank you. I think we have had a lively discussion, and let's thank Varun as well as all the speakers of the session for a very exciting.
Let's thank Professor Dipankar for nicely conducting the session. Good afternoon. Welcome to the last session of 3 days conference. This is the scientific session 9. This session is going to be chaired by Professor Ajit Kembhavi. Professor Ajit Kembhavi is one of the founders and has been the director of IUCA. No need introduction, further any introduction. He is involved in multi-dimensional astrophysical domain. He was the member of ATCOS, highest science body of ISRO till 2017. After that, he became the member of Apex Science Board, renamed ATCOS to Apex Science Board. Still, he is a member of that. I welcome Professor Kembhavi to chair this session.
Thank you very much. Like Anuj has said, this is the last set of talks of this meeting, which has been particularly fruitful with very brilliant talks. So I'm sure that same standard will be maintained now. The first talk is by Enrico Bozzo of the University of Geneva, Switzerland. Enrico.
Okay. Hello, everyone. I hope you can hear me. So first of all, I would really like to thank very much the organizer for the opportunity of being here, celebrating the 10 years of operation of AstroSat with you. This has been a great success, so congratulations. And my contribution to this conference is a modest scientific talk focused on this very specific class of objects, which are called the supergiant fast X-ray transient. By at least, I hope to make this of interest for all of you. I'll do my best. So let me first give a brief introduction. So what is a supergiant fast X-ray transient? So usually we define these sources as a subclass of a much larger source of object, which are called the classical supergiant X-ray binaries. So these binaries are usually comprised by an OB supergiant, so one of these stars with a very massive, powerful winds, and then there is a tiny neutron star, which is actually doing all the job in X-rays because the neutron star is capturing this part of this strong wind. And since these objects are relatively young, only a few million years old, the neutron star is strongly magnetized, and typically, the bulk of this material is accreted on the magnetic poles of the neutron star. Here, the temperature is rising, and you have X-ray luminosity emitted from here. Now, of course, as it was shown for other kind of X-ray pulsars, also in this case, we do expect that the X-ray luminosity is modulated on the spin period of the neutron star, and also you have typically these features like the cyclotron resonance scattering feature, which can give you a measurement of the neutron star magnetic field and appear in the X-ray spectra of these sources. Now, what is the difference between the classical supergiant X-ray binaries and this very peculiar supergiant fast X-ray transient? Well, this is summarized in this slide. You can see on top here, this is the light curve of the prototype of a classical supergiant X-ray binary, which is called Vela X1. This is a system with a 9 days orbital period, and you see that the light curve in X-rays is flaring up and down all the time. All the time means that we have typically a variability in X-rays of a factor of 20 to 50 on time scales that range from a few seconds up to 1,000 seconds. How do we explain this variability? Well, we know very well now, in collaboration with our colleagues working on isolated supergiant stars, that this is most likely, almost certainly, let's say, due to the fact that the neutron star in this object is not accreting from an homogeneous wind. The wind is highly structured. It's called a clumpy wind. So it's a wind made with regions which have a higher density, which are called clumps, typically also a lower velocity. And then there is an intraclump medium, so a medium with a lower density and a higher velocity. So you can picture yourself that every time the neutron star is hit by one of these clumps, one of these bullets, you have a rise in the X-ray emission because the density is higher, so the mass accretion rate is higher. And when you move into the intraclump medium, you go down because the accretion is lower. More or less, it works like this. Now, if you look at the bottom of this slide, you can see immediately that this is the light curve of IGR J17544, which is actually the prototype of the supergiant fast X-ray transient. Now, what is absolutely incredible, and it's something that we still don't understand, you can see that despite this object is very similar to Vela X1, we have the same kind of source of a supergiant, we have a neutron star accreting, we have even similar orbital period, but for some reason, while the average luminosity of Vela X1 is up here, 4 times 10 to 36, then all the supergiant fast X-ray transient, they are dramatically subluminous. With dramatically, I mean something like between 1,000 and 10,000 times fainter than this other source. So you can see that the light curve is indeed much fainter, and then we have this typical outburst of an SFXT, which goes completely out of scale. So instead of having a variability, which is a factor of 20 to 50 in X-rays, here the variability is 10 to 4 to 10 to 6 in only a few hours. So this outburst goes off in a few hours and then is completely gone. It happens randomly across the year, a few times per year, and it's absolutely incredible, completely different from the behavior of classical system. Now, what is also interesting is that if you zoom in the faintest part of the light curve, you can still see that the behavior is pretty similar to Vela X1. So you see that despite this outburst, and you go to the faint part, is still going up and down all the time. So what we believe is that even in these cases, of course, the accretion is occurring via this clumpy wind, because this is an intrinsic property of the supergiant. However, there is some more mechanism which is suppressing accretion for most of the time by a huge factor, a factor of 1,000 or 10,000 or so. So since this is a kind of mission-oriented conference, I also wanted to link the knowledge that we gain on these sources with the different missions that help us exploring this object. First of all, I have to mention Integral, because this is really the satellite with which these sources were discovered. So you can see here a sequence of 4 40 minutes long images of Integral, where the source appear and then very quickly disappear from the detector. So the reason why these sources were discovered, basically all of them with Integral, is because it had the right sensitivity and pointing strategy. So looking at the same region of the sky, big fraction of the sky at once for several days in a row. And actually, today we are not only celebrating 10 years of AstroSat, but we are also celebrating 20 years of discovery of supergiant fast X-ray transient. And in 20 years, we still don't understand the mechanism, the key mechanism driving the incredible X-ray variability of this object. So one can say, okay, these are very interesting objects. What makes them peculiar and of interest for a large community? So let me start from the bottom of this slide. Here you can see that, as we mentioned before, these objects contain a strongly magnetized neutron star, 10 to 12 Gauss, but even more, possibly 10 to 14. And so they are, as all the X-ray pulsars, very crucial laboratories to study accretion, especially wind accretion, in a regime which is strongly magnetized and also under strong gravitational condition because of the strong gravitational field of the neutron star. But more importantly, something that makes these sources very interesting is the fact that basically they can use as you can use the neutron star in this object as a probe in situ to measure the properties of the massive star wind. And specifically, we can measure the properties of the clumps. So the properties, I mean the mass, size, ionization state, velocity, and so on. And why these are unique compared to the classical system? Well, here is the trick. Since these objects are very faint in X-rays, it means that the wind of the supergiant can arrive basically unperturbed very close to the neutron star. The luminosity is low, so you are not photoionizing the wind as you are doing in Vela X1, and it means then that you can reverse engineering the X-ray observation in order to obtain the measure of the clumps. Now one can say, okay, but why do I care so much about clumps? Well, the point is everybody should be concerned about clumps, because this is a very key parameter in modern astronomy and astrophysics, and I can explain this in 30 seconds. The point is, massive stars, of course, are key players in order to drive the chemical evolution of galaxies and also on the universe on a larger scale, because they are polluting with these winds the galaxies with heavy elements. Now, what happens is that the way in which we estimate how this pollution occurs, is strongly dependent on the clumps, because if you don't know the properties of the clumps, then you can make mistakes on the mass loss rate from these stars, which can be a factor of 10 or higher. So it means that not knowing the properties of the clumps leads to high uncertainties on the mass loss rate, the chemical evolution of the galaxies, also the way in which these massive stars explode, which of course is of interest also for other fields, supernovae, gravitational waves, and so on. So clumps is a fundamental brick in the whole process of many different astrophysics topics. So, which is the next mission that we have to be grateful for to understand a bit better these sources? Well, the next online that I want to mention is Swift. This was very important for two reasons. First of all, because with BAT, we could continue discovering outbursts of these sources, monitoring a large fraction of the sky at once, and with the high sensitivity of the XRT, the X-ray telescope, we could monitor in a very flexible way, so exploiting the flexible schedule of Swift, these sources across the years. And what we learn is that despite different orbital periods, they all behave more or less the same. If you look carefully at this light curve, let's do it in the next slide, you can recognize different accretion state. So you see these vertical lines are the outbursts, only a few hours, and they occur only a few times per year, completely randomly. Then you have a very faint emission state that we call quiescence. Note already that the X-ray luminosity between quiescence and outburst is over a factor of 10 to 6. This can go as low as 10 to 31 erg per second, like a very faint star. Then you have an intermediate state, which is between 10 to 33 and 10 to 34 erg per second. And finally, if it was not enough, you also have flares, which is something like the outburst, but a bit less bright, so something around 10 to 35 erg per second. So it's very rich phenomenology. Now, each of these states require a different mission if you want to study them. For example, the outburst, it's mandatory to study them with Swift because they faint down in just a few hours. The bulk of the luminosity is gone, so you don't have time to replan any observation. So with Swift, you get the outburst with BAT, and then you can immediately slew with XRT, and you can get the way in which this outburst is fainting down, sometimes reflaring, and so on. Now, the price to pay is that the effective area of XRT is quite low. So at best, you get a very nice broadband spectrum, but it's difficult to go beyond that, like doing timing analysis, for example, of time-resolved spectroscopy. It's very, very difficult. Something which is absolutely of interest is that in the past we detected what we call some superbursts. So outbursts that can reach a luminosity which are formally impossible in a wind accreting system. It means that you need to explain this high luminosity a kind of temporary accretion disk which is forming around the neutron star and is dissolving in a matter of hours, which is quite impressive. I mean, we have no idea how eventually we could have that. Another game that we can play, which is very interesting, is what we call the cumulative luminosity distribution. These are built with integral, and basically what you do is that you simply count the number of times that you detect the source at a certain luminosity. And you can see that if you take the classical system, Vela X1, you basically get almost to 1. So it means that with integral, you are able to probe all the emission state of the source apart from 20%. And the 20% is because VLX1 is an eclipsing system, and during the eclipse, integral cannot see that, it's not sensitive enough. But if you play the same trick with the SFXTs, you can see that with integral, we are not able even to probe just 10% of the emission state. So these are indeed dramatically subluminous for some reason that we don't understand. The same game is even more fun if you do it with Swift, because it's much more sensitive. You see the classical system, they have this typical shape. You almost get to 1 with Swift, but if you do the same trick with XRT, you can steal something very interesting. So first of all, we are far from reaching 1. So even with XRT, we are unable to probe the faintest emission state. And also you have this kind of typical steps, which highlight the fact that in these sources, there are different accretion regimes that we don't fully understand yet. So what comes next? Of course, the other important mission that we use is XMM Newton and new stars. These are very important if you want to study the faintest X-ray state, because those are inaccessible to any other mission, basically. So what happened, for example, if you want to study the intermediate state, which is the most common one? You can see that this state looks very similar to VLX1, as we anticipated before. It's flaring up and down all the time. It can be explained with the clumpy wind, although we still don't understand why this is 1,000 times fainter than VLX1. But if you are lucky enough and you get a flare, not an outburst, but a flare in your field of view, just completely randomly, while you're observing the source, and you're also lucky enough that XMM is not completely saturated, because that's of course a problem, you can do some time-resolved spectroscopy with the large area. You absolutely need a large area to have an integration down to a few kiloseconds. And actually, without going into the details, with this you can really demonstrate that this kind of events are due to clumps hitting the neutron star and then moving away. Also, of course, what you can do with XMM is to study the faintest ever emission state, the quiescent state. You see the source is barely detected, but what is incredible is that in this state, you are going to see some soft emission component, which is not coming from the neutron star. This is coming from the wind of the massive star. So it means that in quiescence, for some unknown reason, accretion in this object is completely blocked, and we see the naked wind of the supergiant. So this is as well as we can study massive star winds using this object. New star, of course, very, very briefly, this has the advantage of covering the broad energy range up to the hard KV. And of course, one of the goals with new star is to hunt for this cyclotron resonance scattering line. This is a very nice paper which was published by my colleague Varun here, who also gave a very nice talk yesterday. And this was the first detection ever of a possible cyclotron line. We say possible because we like to detect these features more than once in order to be sure. But what is astonishing is that this line will suggest that the neutron star is a rather common neutron star, something around 10 to 12 Gauss, like all the other X-ray pulsars. So again, we don't understand why they still behave so differently from the classical system. Actually, the source was reobserved later on by us, with me and Varun again, and the cyclotron line was gone, so we could not confirm. But these kind of features, they can also come and go depending on the viewing angle and so on. So we are not able to confirm or rule out anything with this. We should observe it again. There is another example where we found another line, again suggesting a magnetic field of 10 to 12 Gauss, confirming there seems to be nothing special with these neutron stars, so the problem remains. Now, one can say, okay, why all of this is of interest for us? We are speaking about AstroSat and so on. Well, there is an important point that I like to mention here that just came to our mind a few years ago. The point is, among all the facilities I mentioned here, you can still say you forgot two important horses that we are in the sky above us. One is HXMT, which is the Chinese mission for high-energy astrophysics, which is a less sensitive instrument because it's designed like AstroSat, especially for bright objects, to do studies of bright emission and broadband timing and so on. But fortunately Unfortunately, we have one single supergiant fast X-ray transient, which is called IGR J11215, which is the only source emitting, for some strange reason, strictly periodic outbursts every time the neutron star is at periastron. Here you can see the collection of outbursts that were detected at different times across the decade with XRT. And then you can say, okay, but even if I have a lower sensitivity somewhat instrument, but having a good time resolution and a large effective area, what I can do is to try to convince the PI to look at this source for like 3 days in a row, try to catch the peak of the outburst, which is possible because the ephemeris are quite accurate, and see what happens. And here comes the surprise. I didn't write anything here because this is a very new result, which is not published yet. We didn't finish the analysis as well, but we discover with HXMT something which is very unique. It was never considered so far, never observed in any other of these sources, and it was possible only thanks to the usage of a large effective area and good timing resolution, something that you don't have with Swift XRT, because when you observe the outbursts, you have a limited number of counts. And what you can see here is that the light curve of this source during a small interval, here it's only a few kiloseconds, you can see that the pulsation from the source, it's coming and going. So we detected for the first time another incredible phenomenology, which is some intermittent pulsation, something that was known for low mass X-ray binaries, but is completely unknown for high mass X-ray binaries. So why pulsation should disappear every few kiloseconds? This is only an example, but we have other segments in which you can see the same. Now, of course, if you have done this with HXMT and you are a bit familiar with the mission, you can immediately jump to the conclusion that this could be done much better with AstroSat. So the point is here, like, is this going to be a new target for AstroSat to unveil a completely new window of discovery on these sources, exploiting the large effective area, the wide energy coverage, and the very good timing resolution? I put the ball in your court. This is only an idea, but I believe that this is another important piece of the puzzle if we want to understand better this object. So let me go to the conclusion. I think I'm running out of time. I don't know. 1 minute, perfect. Okay, so conclusion. Okay, I wanted to mention that, you know, after 20 years of having studied this very interesting object, we still don't understand the basic mechanisms which are driving this absolutely incredible X-ray variability. The facilities we have at disposal are actually fainting away. You know that Integral has concluded operations in March 2025. Swift has degraded in such a way that it's already a few years that we cannot detect outbursts of this object on board. You can say, well, we have Einstein probe and SWAM, but unfortunately these sources are very absorbed, so with Einstein probe is almost impossible, and SWAM is not always looking at the useful part of the sky. We have XMM and NuSTAR, but these are not useful if you want to study the brightest emission during the outburst, which to some extent is also the most interesting one. And again, we have these two wonderful facilities, also AstroSat, which have not yet been exploited for this object, but could really provide important step forwards. So looking at the future very briefly, the last minute, what comes next? Well, the problem is, as of today, we basically have no yet secured mission to succeed and detect new outbursts and actually monitor efficiently the high energy sky. We have Theseus, which is a mission we are planning with ESA, but is far from being secure, is not even selected yet. And so we are going to the impossibility of detecting new sources of this class. We only have, as of today, about 10 of these objects. So we need absolutely a mission to monitor the high energy sky. And then, of course, we need to have a mission in order really to understand the physics, which can provide a large effective area, good timing resolution, and also a large effective area in order to provide this time-resolved spectroscopy, also detect pulsation and synchronous resonance scattering features. You can say that we have new Athena, but this is only coming far in the future, also is not broadband. So I like to conclude my slide with a name, and you will hear more about this in the coming talks, so please stay tuned. Maybe this is the time for ICSAT to finally come. Thank you very much.
Thank you. Time for just a couple of questions, please.
Yeah, thank you, Bozo. The interesting source you pointed out with pulsations coming in, going off. uh, is there a possibility that there is a contaminant nearby within the field of view that could be contributing to the pulsations, photons from a nearby source?
No, no,
That has
that's
been checked.
excluded. Yeah,
I
no,
see.
no, the pulsation are coming from there, and also we ruled out any possible instrumental effect. So this is really a true disappearance of pulsation. You can see you can see with naked eyes, and here is completely flat. Is the pulsation here. So these are each pulse is 187 seconds. So it's rather yeah, it's short. You can detect it well.
Thank you very much for a very nice talk. The next talk is by Santosh Vadavale of PRL, who of course needs no introduction. And you'll see that he's going to be talking about future prospects in addition to the current status. And everything which comes this afternoon after this will be regarding future prospects.
Thank you very much, Professor Kimbavi. And I would like to start with thanking organizers to give me this opportunity to talk about Beyond AstroSat. I went ahead. Yeah. So Beyond AstroSat in our 10th years of celebration of AstroSat. So this is something which is, I think it's a very unique chance for me, because I have been also associated with AstroSat for last 25 years. So it's kind of very, in some sense, a nostalgic moment, and in some sense, proud moment, and in some sense, a heavy moment, because it gives a kind of responsibility to carry on the legacy. And I hope that I will be able to convey whatever, so the idea was to actually review what are the kind of instrumentation activities are going on right now within the country at various places, and how that can be connected to our next possible missions. And so this basically I am going to talk about on these activities on behalf of all the groups which are working in India right now on development of X-ray instrumentation. And I hope I will be able to do some justice. In some sense, I would consider it slightly worrying that after 10 years, right now we don't have a concrete plan, but probably I will try to explain the reasons, and still I would suggest that towards the end that we do have some a good plan in place for at least another 10 years. So let me begin. Just the quick outline. I mean, I will start with this vision of ISRO, what ISRO has thoughts for next 10, 20. In fact, the slide probably you would not have seen it. It actually talks about 62, but we will not go that far. But at least till 2047, there are some thoughts. And then in terms of instrumentation, what are the present activities? And then also we had in between some concepts of slightly quicker turnaround missions, particularly because our major task which we have taken up for a broadband X-ray polarimetry, which is actually focusing telescope, it's taking little time. And then finally, I will conclude with this concept which we have come up recently. Enrico just mentioned towards the end of his talk about possibility of having this large area timing X-ray spectroscopy mission, possibly with the international collaboration. Sorry, this is opposite. Yeah. So just as I mentioned, I mean, this actually Beyond AstroSat activities or discussions had started in some sense well before launch. If I remember, I think many of the participants of this meeting, which happened in 2011, it is getting hidden here behind the timer, but the first meeting was in Ayuka. Professor Dipankar Bhattacharya had organized that in 2011, and I believe almost all the participants of that meeting are here in this room. And we had started discussing about what we should be doing post AstroSat. Subsequent to that, number of further meetings were held, and I think Dr. Sita were there in a space science office at that time, and then that resulted in this particular announcement of opportunity by ISRO, inviting proposals for next generation of astronomy missions. Further on that, there were various activities by ISRO. Particularly, there was a Chintan Shibir about thinking about future 2023, in which I think it was a kind of thought that we require a larger community input into our planning, and then as a result, this pretty massive exercise of SSRF, what we call Space Science Roadmap Formulation, this was carried out in April 2024. I think most of us have participated in this, and there has been a quite voluminous report as a result of this exercise. And then just last year we had another Chintan Shivir which has actually formed up the plans, and then as a result, sorry again I'm making mistakes. So this is right now just one picture which I took from this report, which actually tells us what are the kind of thoughts ISRO internally would have about how to go forward in terms of astronomical missions. This is not only X-ray, of course, it covers variety of infrared, optical, UV missions, including, let's say, for example, immediately exoworld missions, then later on exoplanet finder missions, etc. What I'm going to do is only focus on these X-ray missions, where what has been identified is a specific set of AstroSat follow-on missions which are envisaged. Again, this is again not a one mission, but a series of missions. In fact, the report lists down some 4 or 5 different ideas. And so essentially what I am trying to say is that from ISRO side, we have a kind of a full support and also anticipation from community that that community will come up with a kind of concrete mission proposals. The actual adoption of that would, of course, depending on the various technical feasibility aspects, which will be taken up by ISRO once we have some mature proposal. So this is the idea in terms of agency level support. Now if I go to what are the actual activities happening, I'm just showing this one slide which kind of encompasses most of the activities which are presently going on. Again, I'm kind of split. So as I said, this particular announcement of opportunity was a kind of a well-defining moment. So then as I said before, AO also, there were some activities were going on, particularly at these centers. TIFR has taken up this hard X-ray optics development as a kind of logical succession after SXT, and at PRL we had taken up a development of a focal plane detector, and also X-ray polarimetry instrumentation was at RRI, which is now finally culminated in the form of POLIX and EXPOSAT. So some of these things again led to the kind of announcement of opportunity where there were many proposals, but 4 of them were from X-ray astronomy, 3 of them involving a kind of a focusing telescope. So subsequent discussions led to one joint broadband X-ray polarimetry mission proposal. Jointly, in a sense, basically right now there are these 3 groups, PRL, RRI, and URSC, SAG. So this particular mission was taken up. And then because X-ray optics, I think most of us will realize that it's a very challenging task. So ISRO had again set up a committee to oversee this development, and then as a result, some of this kind of division has been planned. I will just show one slide on each of them later on to give idea about what is going on. The other important proposal was in response to this AO was Daksha, which I think most of you have heard a number of times in this conference earlier. I will just also show a couple of slides on Daksha, what is the status and how we are going about it. But at the same time, since one more thought had originated from Space Science Office, particularly where Dr. Shikumar was there, that since the other major mission which is going to come up is involving X-ray optics is going to take a little longer time, why can't we think of a more focused short-term, slightly smaller medium-scale missions? And then there were some multiple concepts we have been deliberating, and some of them are actually being taken up in a very near future for a demonstration experiment. So I will just show one slide on each. But more interesting aspect here is now that we will, so many of them, some concepts are actually going to feed up to this particular concept which we are now proposing, a large area international X-ray spectroscopy mission. Some of the new activities are taken up. So all of this is likely to culminate if we can take it up for actually fruition. In terms of X-ray instrument, there is, I think this line might not be visible to the audience, but for planetary and solar missions, the X-ray instrumentation activities are very strong going on in PRL, SAG, and all of them have kind of fed to all this part. So this is, of course, it goes without saying that we have sort of a strong community, okay, not small community, but a strong activities in X-ray instrument development. Okay, I have taken most of my time here, so next slides I will kind of flash a little faster. So just to mention, so Daksha, I will not spend too much time here because Varun had very nicely explained yesterday the requirement. Basically, this comes down from our GRB and EMGW studies with CZTI. The lesson learned are that we need to have continuous sky coverage, wide spectral band, and much higher sensitivity. All of this gone into the design of Daksha, and this has been proposed. It has been taken up, reviewed, and now it is going in a slightly serious level. Most important point is that there is also considerable interest from international community in this kind of mission. In fact, there are some formal letters supporting this mission from various agencies are also there. I think Varun is going to discuss a little more on this in a panel discussion. And in terms of present status, if we see, there were three, okay, I didn't show here, but Daksha consists of actually 3 different types of instruments. And if we see the lab models, we had done a good, reasonable development of it some time back. And then, so we are right now, what we are doing is kind of improvising some design aspect of it while we have time. And in the meantime, now URSC has now constituted a formal study team for studying mission aspect. We actually hope that this will be approved and taken up as a mission soon in the near future. So this was about Daksha. Similarly, if we see for a broadband X-ray polarimetry mission, this was kind of considered as a next major X-ray astronomy mission, community-oriented proposal-driven mission from ISRO, 1 to 80 kV focusing X-ray telescope. There will be 2 or 3 different telescopes with a primarily polarimeter as a focal plane detectors. As you know, I mean, hard X-rays, right now we have only NewStar, so this could be the only successor for that. International level also, there have been some proposals, but none of them have accepted, none of the accepted projects have actually the hard X-ray telescope as of today. So if we can do that, this would be very good. But of course, X-ray optics is the main challenge here, and I will just show a couple of slides on that later on. So just to quickly say, I mean, again, most of us know X-ray optics, grazing incidence optics. The main point in this case is that we require ultra smooth surfaces with a multi-layer coating and a segmented optics, particularly because we require coating on the concave surface. These are kind of very challenging activities. We have been doing, so the main point in this case, because we require a large number of shells, each shell needs to be very thin, and for a very thin substrate, when we are trying to polish it for angstrom level polish, it becomes very challenging. So there are some of the main, these challenges are like to develop this substrate. Design aspect, anyway, we have been working, there are a number of software tools developed. Some of these are actually available open source. Maybe if some younger students want to try this out, I think this DarpanX and DarsekX, these are available on GitHub. You can try this, a very nice learning tools. To actually fabricate the substrates, we had explored a couple of techniques. One is a thermal slumping of glass sheets, which is actually done for NewStar optics. We were trying to replicate it. We have done it, but the yield is relatively low in this process. We need a better alternative. But the most important breakthrough which we have achieved right now is at URSC in terms of this electro-nickel replications, where they have actually able to make the full shell nickel shells with required surface quality and figure. So this is something which is very important development. We are actually now trying to see that this replicate same for segmented optics very soon. And if that works, then that could possibly be our baseline design for our next optics. For our actual other multi-layer coating, we have set up a process at PRL, and we have a reasonable handle on that. We have actually done a lot of measurements. So this is actually the example of the curved mirror which we had fabricated using this slump glass, and then we have this coated with the multi-layer coating. Assembly is another, precision assembly is another important task, which is a part of our work segregation. This was RRI group led by Vikram had taken up this task, and they have started some preliminary work. Of course, this is little later in the overall process. So right now they are starting it slowly, but I mean that exercise is going on. So the main point is that though we have made a lot of progress, it's still going to take little time to finally actually come up for a mature instrument design on which we can conceive a mission later on. So that is one aspect I wanted to mention. In terms of focal plane detector, if you see, as I said, this activity was actually started well before launch AO, and then we have actually fully fabricated the focal plane polarimeter, well tested, compared with simulations, and so there is absolutely no uncertainty towards it. Recently, URSC SAG has been also designing this soft X-ray polarimeter, which is based on the TPC, what is called time projection chamber. These are the same gem detector which are used in present IXP mission, but this is a different configuration where we are not using them as an imaging mode, but rather in time projection, so it's a 1D imaging. And they have done a very good progress on it. I will just show later on one concept where this is being used as one of the technology demonstration experiment. So these are focal plane for polarimetry. If we are interested in maybe some kind of other focal plane, as I said, many of these instruments have already been developed for a non-imaging spectroscopy, and it is very straightforward to convert them into optics focal plane detectors. And similarly, if you want slightly better configuration of imaging spectroscopy or Compton spectropolarimetry, those things can also be done. So collectively, kind of, we are thinking that focal plane detectors are not too much of a issue at this moment, but optics design is what is going to take little time. So in that context, as I said, we had this suggestion that why don't we explore the possibility of a smaller mission which can be done little quickly, and then basically to sustain whatever momentum generated by AstroSat. And then in that context, we had these 4 different ideas which we have been exploring. All these 3, the concentrator, soft X-ray polarimeter, and hard X-ray polarimeter, are actually being taken up for a demonstration experiment over in a very near future, maybe near in a sense, I would say 1 or 2 years. This expect XSL was a kind of an interesting idea where the present expect, which is there on AstroSat, maybe you could have actually simply made a slightly larger version of it to cater immediate requirement for a community. This, at that point of time, it was kind of thought infeasible because of the detector availability issues. But now we hope that this same concept will make a comeback in terms of a new version, which we are going to talk, which I will just show one slide, and Enrico mentioned briefly. So I will show it a little later. Not in the name expect XXL maybe, but this is the concept which we are now thinking that it could be a much larger collaborative mission. So just to quickly show, so this is one soft X-ray polarimeter planned for upcoming tech demo mission, where this is, as I said, TPC based configuration. The basic idea is to actually demonstrate the engineering aspect of the gem based detector, and also to see the environment effect and kind of actually estimate various particle backgrounds, because as you know, based on our POLIX experience, for polarization measurement, the background is very, very critical. And these are just rough specifications right now. We won't go into too much detail, but this is being taken up for the mission, and in the very near future, it is likely to actually launch. Similarly, there is another concept for hard X-ray polarimeter. This is a slightly evolved version of our focal plane polarimeter which we had developed. We had conceived collimator detector, a large area array for astronomical purpose, but one of the unit is being designed for applications of, again, sun as well as bright X-ray sources, and this has been accepted for microsat 2D mission, again, which is supposed to be launched, I think, early next year. And so this can do some good solar science, because sun is a very bright source, but also it can address some crab-like source for X-ray polarization also. But the most important point is that it will give an idea of how actually we will be able to do the hard X-ray polarization measurement in space if we have a larger either focused or collimated detector, because the background is getting very critical, so that we will have first-hand information with this. And as you can see, this has been kind of one version lab model has already been fully built. We are now working on the actual flight model of that. The second version which we are working is a kind of slightly new concept, where because our actual focusing optics with the curved mirror is getting little tricky, what we came up with a different concept for a concentrator, because in X-ray astronomy, most of the time you are not interested in extended sources. Most of the compact objects are point sources. So if you can simply concentrate using a flat panels, that would also serve. So this is some revised configuration of what we call Schmidt configuration, which is meant as a kind of wide field monitor, but we can change the angle such that it will work as a focusing detector for on-axis sources. This has been verified experimentally, and we are now making this as a kind of proof of concept payload for upcoming microsat mission. One important point is that these also we are thinking for our next large area mission. So I will just come to this last slide, where recently, I think year and a half ago, we had this discussion with our European colleagues, and they were interested in trying out this kind of collaboration, where many of the community would know that this is the detectors developed for a loft mission, which has or very large area detector spanning about a meter square, maybe few meters square. Originally, when loft started, it was 10 meters square. Slowly it was around EXTP around 4 meters square. So they were interested, if from our Indian community, if we are interested, they can also are ready to collaborate. So we are taking that up at a further level. In fact, recently also we had a lot of discussions with Enrico. So at a community wise and as a scientist level, we are all on the same page that this would be a win-win for both. And so we are just hoping to initiate at a slightly higher level discussions on this. Overall feedback we have discussed with a lot of colleagues is very good. So, but we will see how to proceed. In which case, as I said, that SDD detectors basically will come from Europe, but then we will also have another supporting instruments for the concentrator. So, where we are thinking of array of this kind of concentrator, and also since this wide field imager is being designed in RRI and SAG, so broadly we will have these kind of specifications where typically around 5 meter square SDD, which you can see how big that would be and how much advance it would make. It's one order of magnitude higher than LEXPC, plus a very high resolution X-ray spectroscopy. And we have a lot of confidence on this because these studies have been done by both for various missions, LOFT, EXTP, and recently STROBEX. So this is very good potential. This will be a nicer like concentrator array, and this will be a wide field imager. I'm showing in slightly different color because these are the overall mission numbers, whereas this right now I'm showing only for one of the module. The actual configuration will evolve a little later. This just shows some quick simulations of how much improvement we are going to see. You see one crab, we are going to see like very nicely. So this will be a truly game changer in my opinion, and I hope that we should be able to get it. So I will just summarize it here. As I said, AstroSat has been a very powerful catalyst for Indian X-ray community, and we should continue that momentum. I just wanted to mention one sentence because we have not discussed AstroSat too much here. But one, we need to see that this is absolutely first mission in the world to attempt this polarimetry, and this has given some very, very interesting result, if not from astrophysical point of view, but at least how to carry out X-ray polarimetry, because it has first time shown that the background is actually not only kind of a polarized modulated background, but how the modulation changes as a function of time, that part is given. So I think this has yielded very important result. But the polarimetry itself is a very niche and a very long exposure demanding measurements. So I think it would be very good to have this kind of a broadband large mission for timing spectroscopy along with the Daksha, where Daksha is actually going to serve as a true all-sky monitor both for GRBs and possibly with some improvement which we are thinking for Daksha as a real X-ray transient monitors. And so I hope within next at least a decade or so, we will have a very good plans for Indian X-ray community, which will have really worldwide impact on the X-ray astronomy from Indian side. So I will just stop here.
Thank you. Thank you very much for a very powerful talk. Very forward-looking. Questions?
Your description can either be thought of as wide spectrum or confusion. What is it?
No.
What is it?
Okay, so final conclusion here, what I would suggest is that we need these two different missions. One is Daksha and the one is large area X-ray spectroscopy. So this right now, I think if we all push together, it can be realized, and this is what should be our next step forward.
Long term means what? Long term? 2 generations or?
I understand what you are saying, and then I was actually hoping that we don't have to discuss that, but then everybody knows that. So this I'm just putting as an order, no time.
Everybody knows what?
Time scales. I mean, how much time scales are going to be taken. So what is the meaning of near term, mid-term, long term? Could be different for different people. Finally, what we realize that's what we have
that
to
also
see.
keeps evolving. Yeah.
This time scale may be critically dependent on the last line, which is hidden from the most of the audience.
It's a most
which
hidden.
Which is major limitation, subcritical mass. Okay. So I haven't started my question. Okay. Now, since now, as you told, very few centers like maybe PRL and URSC. So you have many works as you described, as Randan was commenting that it's going on, time is going on. So have you thought of compartmentalizing, articulating? For example, if say third party like IIT Indore or this one, is there a website where these things are described and where they can pitch in? So such thoughts and
yes,
such
I mean,
actions have you been?
Okay, so there are two things. One is I personally have sort of a fair clarity in terms of how to go about it. I have discussed with some of the colleagues about how to go about it. We have not put it up as a website or not as a formal document, only because we are just kind of looking for, if it really gets kind of a go ahead, let's say at certain level, if we have internal confidence, yes, we are taking it up, then we will certainly take up what you are suggesting, and that is how it will be done. Without that, it is not possible. Particularly, I can identify right now the pockets which are outside these centers and ISRO, which we are actually trying to capitalize on activities on there, particularly various IITs, various universities and all, wherever we have the active X-ray astronomers right now working, even if they are whether involved in instrumentation or not, but at least taking their help in using some of the other colleagues at that center or students at that center in terms of understanding the peculiarities of the detector calibration, how we can utilize. So internally we have some idea, but and then that is what is the plan that we will try to take up.
We'll come back to this at the end of the panel discussion. Thank you. So the last talk.